Good morning. Ilya, can you hear me?
Morning, morning. Yes, I can hear you.
Yes. Yeah, I just wanted us to test the audio and
Mhm.
to see if screen sharing and everything is fine.
Okay, okay, okay. Now we just tested already screen sharing. Let me, oops. Okay. Can you see my screen?
Yes, yes, it's in full screen. Perfect.
Okay, very good.
Okay. We will start in 3 minutes.
Okay, okay, okay.
And do you have Slack open?
Uh, I because I'm in a full screen, I could not see
Ah,
what
you cannot see.
yeah,
Yes.
yeah.
Okay.
I have a Slack open, so if there is some issues in Slack or questions in Slack, somebody just need to tell me so that I need to check what's happening in the Slack. And
Okay.
I will be able to check it. I have it open, but I don't see activities on Slack. Okay.
All right. No problem. I'll keep an eye on it for you.
Wonderful. Thank you.
Okay. Okay, good morning, everyone. Again, and according to my watch, it's 9:30 sharp, and today, it's day nine, of our CSS 2026. And I have the pleasure to welcome Associate Professor Ilya Sinaisky, who is a researcher in the Quantum Research Group at the School of Chemistry and Physics at UKZN. And his research interests include open quantum systems, quantum optics, and quantum information. And he's going to take us through some machine learning today and tomorrow. So enjoy and please engage and ask questions. Prof. Ilya, over to you.
Hey, good morning, everyone. Yes, as Tutukili introduced me, my name is Ilya Sinaisky. I'm from UKZN, and I'm a physicist by training, but now everybody doing is a little bit of machine learning. That's why and I'm also one of those who's doing not only classical machine learning, but also a little bit of quantum machine learning or classical machine learning towards, quantum physics or quantum computing problems. And that's why I'm going to tell you that so if I have some ideas about machine learning, and I'm going to give you a little brief course on traditional kind of like introduction to the machine learning. Yes, and my slides will be based on the lecture slides from some applied machine learning course at Penn University from United States, which are available publicly. So if you want to dive deeper, you can always do something like that, or there is a zillion and one course on the YouTube. As I mentioned, because I'm in the full screen mode, I will be unable to see what's happening in the Slack. My Slack is open, but somebody will need to tell me that I need to check what's happening in the Slack so that I can check it. Okay, and if you don't mind, I will likely to turn off my video because I just get the message that investor they have a little power outage, kind of the lower power, and that's why the university turned off aircon system, and I'm slowly starting feeling it. So I don't think that it's a. So I will just turn off my video, not to not to embarrass myself in front of you guys. Okay, uh, if I find the button to turn off my video, yeah, okay, good. Okay, so what is machine learning and what are we going to talk with you about? And there is a several definitions of machine learning, and according to the people who started all the business of machine learning, so we have several opinions. For example, what is machine learning? It's a learning of any process in which system improves its performance from experience. Yeah, it's an interesting statement. Sounds a little bit like humans, yeah. So we improve our performance from experience, yeah. But we can also try to formalize it a little bit. So because as machine learning as a part of the formally speaking computer science discipline, and words are words, but sometimes in order to make a progress, you need to formalize it. And the one of the typical formalization is looking like this. So machine learning is a study of algorithms that they have some performance which should be improved at some given task with some experience or training data. So essentially, one can speak about machine learning in generic sense when you have these three categories are um, presented to you. And we are going to talk a little bit about, kind of like what is a performance and how we measure performance, what kind of tasks one could have, and kind of like we're not going to spend too much time on training data or experience because experience have a relationship to one of the forms of machine learning, and training data have relationship to some other types of machine learning, which we are going to discuss just now. And the typical example is, for example, yeah, kind of a spam filter. Yeah, so the performance is classify emails as a legitimate or spam. It's a type of what is called classification problem. Yeah, so is it legitimate? Is it email which I or you supposed to see, or is it email which we shouldn't see? Yes, legitimate or spam. That's a task. The performance by which we are going to evaluate the model is, the percentage of the emails which are labeled correctly, which include, of course, labeling legitimate emails as a legitimate and spam emails as spam. And also kind of within that, because it's a part of the classification problem, we're also going to look on the um, uh, metrics, how you can evaluate it, and very typical metrics, for this kind of problem is related to the object, which is called confusion metrics, but we are going to speak about that later today. Okay, and and what is the training data in this case? The training data is a repository of the typical emails, so kind of what is a typical legitimate email and what is a typical spam email. Okay, so this is the example of this triple of the performance, task, and experience. And another from the other part of machine learning is, for example, playing games. Yeah, so we all know that modern machine learning systems are very good in playing games, and it's not only chess or Go, it's also several kind of like Atari type games and so on. So kind of and supposedly, yes, machine learning systems are extremely good at it. I mean, essentially, and they are on the superhuman level. So essentially now the question is not standing, is there a human player which can beat the state-of-the-art chess machine? And the answer is no. Such humans do not exist and probably will never exist. Okay, so the task is, of course, playing chess or some other game. What we're going to improve in performance in that case, it's percentage of the winnings against the opponent. And in this case, very interesting that the training data is training data in kind of like in the modern version of, I don't know, the chess game or chess machine learning systems or the Go machine learning system. Essentially, the algorithm is played with copies of itself. It's don't even need any more, don't need input human data. In original chess programs, the one which beat the Kasparov in 90s, over there, you need an input of a lot of human games. But in the modern version, which is, for example, developed by the famous DeepMind, you don't need it anymore. So the computer just, so machine learning algorithm can just play it with itself. And after some time, it reaches, it's getting better and better in playing and reaches a superhuman level of the efficiency in playing. Okay. One more option on what is a machine learning, and this is also a very interesting opinion or kind of a definition of machine learning, which leads to the kind of a partial shift in the paradigm in the programming, is machine learning gives a computer an ability to learn without being explicitly programmed. And why this is very interesting, because if we think about the traditional programming, and the previous week of the school was about that, what you were doing, you were formulating task, you are formulating the algorithm of what you want exactly to do. What is exactly you wanted to do, and the art of programming is in formulating, it's in efficient and the understandable and correct way, and so on and so forth. But you need explicitly program the algorithm of execution of the corresponding set of actions. Yeah. While in machine learning, what is happening? We are not programming explicitly the set of actions which the algorithm needs to do. What we will be programming, and what machine learning is doing, it's performance. So of course you need to program the typical structure of the certain kind of what is the model, so to say, defined, and I will specify that just now. But you don't program actually, and it's better to understand on the very simple example, kind of like, so what is the program? So for example, we have a bunch of images of cows and turtles, and we need to write a program which is going to distinguish them. And can you imagine formulate it as an algorithmic task? The task of defining what is common between all of these images of cows and the several thousand more images of cows, as distinct from these several thousand images of turtles. And it's clear that doing it in a traditional way of the programming, it's nearly impossible task, or probably impossible task. While using the machine learning algorithms, which are called convolutional neural networks, or even deep neural networks, will be able to solve this kind of problem. We're going to see tomorrow that this is a rather trivial task which could be done within a few lines of code using specialized packages, and we can get the answer very, very quickly and efficiently, but we could never formulate this function explicitly, cow or turtle, which is going to take an input as an image and spit you, and afterwards by doing some, step-by-step action, as go through the pixels from 1 to n, and if the pixel 1 plus 1 kind of plus pixel 2 is this, then that. So you cannot apply this kind of logic. So the logic will be slightly different, and the logic is essentially will never be programmed, because the logic will be the logic of how the corresponding machine learning algorithm decides whether the pictures of the cow or turtle or whatever any other pattern matching picture will be based on the training program, and essentially the decision making is a little bit behind the shade. Okay, so that's kind of the good things about machine learning. And okay, so I'll do the and what is the typical machine learning problem? The typical machine learning problem is prediction. Yeah, so kind of we've seen already classification, we've seen already kind of recognition problems, but the typical thing again, which we can also say, is a prediction, and that's where the typical machine learning algorithms works very well. And in this example, we're talking about the width of the thickness of the ice sheets, and we're kind of like calculating we have some statistics. Yes, we have some historical data of how the width of the ice sheets is behaving, and the question is, how what will be the width of the ice sheets if the trend continue with the with time. And the question is, how can we formalize problem like this? And you don't need to be, and you don't need to know too much about machine learning if it's roughly going like this down. So one can approximate that it's going to be here by 2025, and of course, it's going to be low by 2026, and so on. But of course, that's create a very interesting question, which will come just now on the slide, so that can we predict something here? Can we predict something far down the range of our data? And the answer is no. Usually machine learning algorithms are not good with that. Okay, so but predict something in the near future that machine learning algorithms are very good at, and we're going to see the examples of the algorithms for that. Okay, so what is a typical machine learning pipeline for prediction, or what is the sequence of action which we need to take? So we need to take data, of course, and what does it specify? Data will depends on the problem. For example, if the problem is classifying of the images, the data will be the images of the, I don't know, turtles and cows, and also with the extra file, which is saying that the image number 1 is the turtle, image number 2 is a cow, and so on. So we need to pick an algorithm which we are going to use. Yeah, and afterwards we need, using the data, train this algorithm to create a trained model. And afterwards, what we need to do, we need to take a new input which haven't been used in the training process and check if it works well. And how to do systematically, that's what we're going to talk about. And essentially, I'm going to spend a little bit time of today on a very, very simple family of machine learning models, which you also heard yesterday about, which are called linear models. And the reason why we're going to spend time on them is because you can explain essentially all the concepts, or all the fundamental concepts of machine learning, which you need to pay attention to on that very simple class of models. And whenever you move to the more difficult models, and in the kind of the tutorials part of these 2 days, we are going to deal with the more complicated families of the models, or also in the lectures we are going to deal with, I'm going to explain to you a little bit more sophisticated models than linear models. The basic ideas will be the same, okay? But before we're going into that, what kind of learnings we can have? We can deal with you with supervised learning, and this was kind of the typical problem, which is for the prediction or many other. So, and what is a supervised learning? Supervised learning that you have examples of inputs and outputs, and the model predicted unknown output given a new input. Yeah. So, in the sense, you have a bunch of pictures of the cats and dogs, or cows and turtle, or of anything else, and you have a label so that this is a cat, this is a dog, this is a turtle, this is cow. And afterwards you take an image which you as a human can of course recognize as a cow, dog, or turtle, and you can give it to the model, and you can see how well it's performed. Okay, so there is another type of very interesting family of machine learning models, which is called unsupervised learning. And in this case, the input is just some data. You don't know what the data is, but what the problem is solving, it's solving so-called structure in the data. It's going to find you the hidden structure in the data, which you're not maybe not aware of. Or it could, for example, help you to compress the data. And this is another very interesting problem which one is going to face then when you have a data which have very many input variables, but you don't know how many of those input variables are really important. Yeah, and we're going to see in the examples that, that sometimes you can very easily say that, okay, the variable 1 and 2 or combination of those is important, but, all the rest variables are not important. Yeah, and so that's what is unsupervised learning is solving. Essentially, yes, it just find the structures in the data, and afterwards it will be the job of you as a machine learning engineer, or kind of the person who's using machine learning, to understand what the structures in the data represents. Or you can use this as an additional input into the supervised learning pipeline. Okay, and the last bit is kind of the traditional. So there are a lot of additional things. There is a semi-supervised learning and so on. But roughly speaking, for the first order approximation, zeroth order approximation, you can split all the types of learning into the 3 camps. And the last one is reinforcement learning. And this is a rather different type of learning. And over here you have an agent which is interacting with the world, and you have a policy which is predicting or which is evaluating the action and reaction of the agent in the world. And the game playing kind of algorithms, they are based on the reinforcement learning. Okay, so supervised learning formally, what does it mean? Supervised learning, it means that, for example, for this kind of problem which we've seen with you with the ice sheets, yeah, so we are supplied the pairs of points, yes, here, and the uh, ice extent, yeah, and xy, and based on this set of points, we need to predict, we need to build a model. In this case, linear model do well enough, and how we understand which model do well enough or not, we're going to see in a few slides. And our task is predict what will happen. Yeah, so this is a supervised learning. Another example of the supervised learning is a classification task. So this is supervised learning for what is called regression task, because the output of the algorithm is the real number. Yes, because it's just some number, and in this case, in the range from 0 to 9. So, oops, sorry. Another type of problem is what is called classification. And this is, for example, kind of the typical classification tasks. Again, we've seen our examples. If you have only cows and turtles, is it cow, is it a turtle? It could be seen as a classification task, yeah? Or for example, in more practical sense, so you can have, what is now very actively used in the medical sciences, and this is one of the kind of examples of early applications of that. So you have a set of images. For example, in this case, it's an image of the retina of the eye, yeah, and based on that one can predict whether the kind of the, and you get this bunch of images with the certain characteristics, but essentially it could be the photo of the retina of the eye of the person with the tumor or without tumor, or what kind of tumor. Yeah, and the classification task is saying, is it a good tumor or is it a bad tumor? So whether the person is required immediate operation or not. So classification task is always, kind of yes, no type of answer. If it's a binary classification, or you could have, the class 1, class 2, class 3, and so on type of answers. So yes, so kind of like, for example, if we would have, again, images of cows, we could have a data set of the, I don't know, images of cows, turtles, cats, and dogs. In that case, we're going to have 4 classes, yes? Class cow, class dog, class cat, class turtle, and so on. And the very famous example of this kind of data set is what is called the ImageNet data set, which I think have 1,000 classes of different thing what is shown in the images, and that have a certain animals, cars, and houses, and several other things. If you just type in the Google ImageNet, you can immediately find it. Okay, so the typical example of unsupervised learning is that we are given some input data, but we don't know what the data is. And let's say that the data could be shown in the 2 dimensions like that. So what the unsupervised learning algorithm, or one of them, will tell you, so that it looks like that out of this data, these points have something in common, these points have something in common, and these points have something in common. But there is much less commonality between the red points and the blue points, and this problem is called clustering. So we can say that, okay, so these points have closer to each other, these points are closer to each other, and these points are closer to each other. So probably it's 3 different things, whatever the things are. And what exactly is making them different, we don't know. But in some space in which we can represent our data in these 2 dimensions, it's really telling us that we have this group, that group, and that group. Okay. So, and afterwards, as a user of the machine learning algorithm, you need to go look into your data and say, what is the common thing between all of these points? What is the common thing between all of these points? And what is the common thing between all of these points? And there are very many applications of unsupervised learning. For example, if you take, that you can find the subgroups in the social network. So you have just, the data of the connectivity of the social networks. Yeah, so you can just see how many you have friends and how many friends your friends have to whom they're connected. So you can build a connectivity graph. And afterwards, one can run unsupervised learning algorithm to find that there is some hidden groups of people who are communicating around certain subjects. Yeah, so famous echo chambers, that's how you can identify those echo chambers in the social networks. Okay, so you can also use unsupervised learning to identify different exoplanets or generally to classify or kind of identify objects which you see, for example, on the images. And you can say that, okay, so these objects have something to do with each other, that objects have something to do with each other, but they're different. And for example, you can again apply to the search of the exoplanets or some other objects. Interestingly, yes, kind of the with the kind of like with the images of the kind of the classification type of images, if you apply certain types of very specific unsupervised learning techniques, you can separate those images, and this is probably some sort of non nonlinear dimensional reduction technique, which probably something like TSNE, which we're going to see as an example in the tutorial on some much smaller data sets. But essentially, you can identify some typical features in the image groups. And yes, reinforcement learning, yes, the kind of the simple image that you have an agent which interacts with some environment, and this environment could be real environment. I'm sure that many of you have seen the YouTube videos of Boston Dynamics type of robots, which are running around, which are jumping and doing other things, because and that is exactly and they have a built-in algorithm of learning, so they trying to do steps and they adjusting this response such that they can walk without falling and so on and so forth. But in the same way, you can have some artificial environment of the, I don't know, Go game or the chess game, and you again looping in this loop to the moment when the agent or kind of your real life robot or agent or kind of the game playing engine or whatever other thing is competent enough. Yes, and also kind of like many science-related examples are related to the fact that you could, for example, stabilize using this feedback loop many unstable systems. For example, there is this many YouTube videos which you can easily search, not only of the robotic arms doing things like that, but for example, that how you can stabilize the inverted pendulum. Yes, kind of or kind of double inverted pendulum, which is very difficult operations to perform or program, but using this reinforcement learning framework, you can run this loop of the try to do the actions, get a feedback, and afterwards adjust your set of actions for the feedback. You can play this game as well and quite efficiently. Okay, so there are several other applications of the machine learning which we are all aware of. Yes, so kind of the spam filters. We also heard about self-driving cars. They're not yet in South Africa, but in US there are already quite a few in several cities. There are self-driving cars so that you can take a taxi and go somewhere without driver. Okay, so of course we know about recommendation engines, or for example, recommendation in the social networks, the smart speakers to assist us with our life and so on and so forth. Of course, we are all aware of kind of like and but that's not only in the kind of like you know whatever the Netflix recommend you is probably not that important for your life. One can survive without Netflix, but there are several practical applications which are really important for people. Is, for example, application in medicine. And what are some of the machine learning algorithms, in particular neural networks or convolutional neural networks, good at? They are extremely good in spotting patterns, and they are essentially in that application of the spotting patterns in the input, for example, visual data, they already surpass human performance. And naturally, for example, in radiology or medicine, you can use train neural networks to at least to alert the radiologist that, oh, there might be a problem with these patients because there is something suspicious on the radiogram. And of course, afterwards, or kind of on the brain scan, and of course afterwards, the medical professional needs to give a look and maybe ask for the additional examinations and so on and so forth. And we all have heard about this, and it's obviously not exhaustive list of the examples. We know that machine learning is now very actively used in scientific discovery. Yeah, so we heard about the AlphaFold, and many people have heard about the AlphaFold. It's essentially a machine learning algorithm which can solve a very difficult problem in the realm of chemistry or kind of in biochemistry, which is related to the thing how the proteins folds, how the chains of amino acids folds to a certain to form certain shapes of the proteins, and kind of like traditional computationally, it's an extremely difficult task. But what have been shown that using a lot of machine learning and the enough training data, you can solve this problem in a very efficient way. And the community, the academic community, was so kind of um, so amazed by this, and it's shown itself so useful, so that the creators of the DeepMind, or at least the leaders of the group at Google and the DeepMind, get in 2024 a Nobel Prize in chemistry exactly for doing that. Yes, of course, there are applications in astrophysics of machine learning, for example, for the denoising images or identifying the unknown objects and so on and so forth. And of course, there is a famous applications of which probably you've seen in every day, is in generating images and even more generating text. And I'm sure that a lot of you have used generating text. And here as an example, because this is based on those lecture notes, and and they give an example of this GPT-2, which is the old text generating thing, because it's something like 2019. And the prompt was, recycling is good for the world. No, you could not be more wrong. And essentially what the GPT-2 model was doing is begin to essentially trying to generate some text which is coherent with the statement. Yeah, and just kind of like in the world of these large language models, the typical thing is how many parameters these models have. And yesterday, just out of curiosity, I decided, okay, so if I do the same thing but on the modern ones, so I just use the ChatGPT 5.2, whatever, in the thinking, even not deep thinking mode. So it's an early 2026 model. We don't know how many parameters does it have, but the estimates are saying between 125 to 600 billion parameters. So between 100 times and 500 times larger parameters. And if you could read it, but if not, the slides are in the canvas. So essentially, it's now not just begin to tell me that just following my prompt, is begin to analyze why am I saying that. It's trying to bring some nuance in the conversation and so on, so you can read the response for yourself and just have a laugh, because I think it's a very nice thing, and it's also quite a nice progress which one could see in this type of models over the last 7 years. And that's why this kind of large language models becoming a more and more useful tool, because now it's at least trying to make some coherent statements and not just generating random text, which seems to be correlating with the prompt. Okay? Okay, but now we come to the slide which I mentioned before. So where is machine learning is or very likely to be bad? And that's what you need to know. Machine learning is not the answer for all questions, which is extremely important, because nowadays you look and you see that machine learning is literally everywhere, and the people are thinking, oh, machine learning, machine learning, machine learning. But machine learning is not very good everywhere. And typical example where machine learning will be bad is what is called out of domain or just far enough data point. The fact that we have a trend here, and we can draw the trend line here, obviously don't apply that in time moment here, which is what it would be in another 50 years, roughly speaking, yes, because on this axis we have a 50 years from 1975 to 2025. Here is another 50 years. We could not have a ice extent here, because it means that it's going to be negative, and it's not even clear what it is. So it's clear that we could predict what will happen here or here, but what will happen already even here is already questionable. So, and this is a typical example, and you can see these examples in many, in many academic publications that, for example, in my domain, I've seen that people were using machine learning for the prediction time dynamics, for example, of open quantum systems. And the universal output was that if you use a little bit of input data, usually the prediction of what happened in a long time of the evolution is not very correct, or you need to do some special tricks to make it work, because that's exactly the situation. So what you need to understand and what you need to know is that, machine learning, as any other software or kind of the computer science tools, is a tool which is good for the one type of problems and bad for the another type of problems. if you want to multiply two numbers, probably, you can just use good old programming as you learned last week, and you don't need to write a machine learning algorithm for that. Okay, so now let's dive into the type of models. Are there any questions by this bit?
No questions so far on Slack.
Okay, good, because in principle, there is nothing new, and it was a little bit of good weather. Now let's go a little bit into the nitty-gritty. Okay, so machine learning for prediction, and as I mentioned, what we're going to talk about, because what is very important here is, you have your data. It could be data from your experiment, or it could be some other data which you have. Yeah. So now you need to pick an algorithm, or kind of you need to pick a model family. What can you infer, or what can you propose of the type of the data which you are going to use and to train machine learning algorithm? And it's not always the answer that, oh, you need to go for the neural network. So because, now what some people are doing is they immediately go for the neural network. But again, you might just don't have enough data to do a neural networks. And what you might opt for, opt for traditional algorithms. And as I mentioned to you, we're going to speak about, or start speaking about, the very simple family of the models, which are called linear models. Yes, and what is a linear model? And you've heard it yesterday already during this week. It's a very simple function. Yeah, so we have some input x, which could be multidimensional, which could be a vector, and in that case, it needs to be multiplied by some vector beta. Yeah. So, and if you input x, if your typical data point have d entries, so your beta is also needs to be vector which also have a d entries, so that your linear function is spitting to you beta 1 x1 plus beta 2 x2 and blah blah blah. And in that case, betas are parameters, and exactly the machine learning task is to identify these parameters such that your prediction on the training data is related good enough to your training data. And what does it mean? We're going to see just now. Yeah, so kind of a little bit formally. Sorry, let me just, okay. So we have a data set of the couples of points, and where each point is the vector by itself. So each xi with the index like this in these nodes means that it's a d-dimensional vector, or meaning that each xi is just d numbers, d real numbers for simplicity, and yi, or label, is the number which you want to predict, and it's also a real number. So the output of the linear function is this beta t on x, such that beta t on x on your input data approximate well enough what is called a label. And we're now going to talk about what does it mean good enough. Okay, so typical notations which are going to be used through these nodes. I is indexing the different data points, and j is indexing different entries of given data point I. Yeah, and of course, if you use index I and j simultaneously, you can build a kind of rectangular matrix, and it will be a little bit useful for epsilon of mathematical calculation, which we're going to do. Yes, and what is the machine learning task is to find the betas such that we have a good enough approximation. And again, what the good enough and how we estimate this goodness, we're going to talk just now, and what are the tips and tricks of how you estimate in the goodness. Okay, so on the example of our climate change type of example, yes, so we have a bunch of points. F of beta is predicting to us a line, and xi is one-dimensional point with the year, and yi is the uh, ice extent. Yeah, so it's so this is our problem. Okay, so now the question is, what does it mean good enough? And in order to introduce what is good enough, we need to introduce a measure of the goodness. A very typical measure of the goodness is what is called mean squared error. And it's a very simple thing. So if this is our, for the given parameters beta, this is our f of x, yes, it's just a linear function, yeah. If it's x is multidimensional, it will be so-called hyperplane. Yeah, you can just imagine a plane in three-dimensional space, or kind of if you go to the more dimension, it will be just also a plane, but in multidimensional space. Yeah, and mean squared error, what does it do? It's measuring the distance from the real answer to this line, to the prediction, yeah, and summing up squares of them and averaging over them. Why this kind of, I mean, this is not the only choice of the measuring of the goodness of your fit. There are several others, but this one is a very easy one to understand, easy to visualize, and it's more important when we are going to see that how we are going to find these betas in a computationally efficient way. So using the training, numerical training algorithms, this loss function is very good. So because it will be so-called differentiable, but essentially it means that, it's going to be nicely calculatable from a practical standpoint, because there are other loss functions which I'm going to mention, but some of those could be useful in some practical sense, but they have a little bit of, they might have numerical challenges. Okay, so again,
Sorry, Ilya, there is a
mhm.
question.
Okay, let me check. Uh, what are some examples of important synthetic data for training of these models? I'm not sure that you know, synthetic data is, okay, it's a data which one is generating. For example, we're going to, but I'm not sure what is an example of important. What the importance is in the person who is doing machine learning. If kind of, I don't know, the questions of the climate change are important for me, I would be probably paying some time to this data, and I will assign an importance to them. But if somebody is saying that climate change do not exist and it's all BS, that person will probably ignore this data. I'm not sure that I fully understand the question, because if importance is a subjective thing. And you should be also careful with the synthetic data, because if it's a synthetic data, you're going to learn the synthetic relationship, which might be good for example, I'm going to give you an example of synthetic data, but you want to deal with the real data, because the real data have issues beyond what the synthetic data can give you. I'm not sure if I answered the question, but I assume that I dodged it well enough. Okay.
Yes, he says he's answered. He'll ask again with more context.
Okay. Okay, good. Thank you. Okay, so we were here. Yes, so we have our input data, and again, X is the multidimensional vector, so it's a bunch of numbers, yes, and Y is just a one number. So, and we want to find list of numbers beta such that it's minimizing this function. Okay, so on the fancy machine learning language, which you could see in some textbooks, so if you decided, okay, that I want to step further and I don't want just to watch YouTube videos, I want a solid foundation in these things, mathematically, it's going to be written like this. So what is the linear regression task in this sense? That you want to find the betas, such betas, such that you are minimizing the argument of this function, and the argument is taken, or an argument is a list of betas. So this is, but essentially, what does it mean? It means that you are minimizing, you are kind of trying out all the betas such that this quantity is minimized. That's all what it means. Okay, and in that case, after you have done this task, you can say that your model, or your kind of predicted model, is looking like this. So it's these betas which are coming through the minimization, and of course, the values of the betas will depend on the how many and what kind of training points you have, because as you're changing training points, your betas will change slightly, and that will be another way which we are going to discuss, that how you need to also to present your results, and what you need to do as the machine learning user to ensure that the result of your training of machine learning algorithm is not a random artifact of the data, but how you can make sure that this family of the models which you choose, for example, linear models or support vector machine with a given, I don't know, kernel or whatever, or some random forest or neural network or whatever, is giving you really the evaluation based on the model performance, and how to take away the problems of the data out of the equations as much as you have. Okay. And now a little bit of intuition, why minimization, why this minimal square, mean square error, sir, is such a good thing. So let's do again a very stupid example, and very simple example, but very illustrative of the synthetic data. So we have a very simple function, y is equal to x, yeah? And we have 3 points, 1, 2, 3. Yes, and of course the correct answer, so to say, is beta is equal to 1. Yeah, so we can perfectly fit the data. Yeah, so and in that case, if we calculate this minimal mean square error, that would be 0. But now if we try a different beta, so if we try a beta 0,5, it will be the straight line like this. So we can calculate the distances and we can calculate the loss, and it will be somewhere here. We do it like this, quarter, and it's going to be here. And we do it also on the other side. Yeah, so we do beta 1.5, 2, and so on, and we're going to get here. And now what we see that what is in this synthetic and very simple example, how the landscape for this guy is looking like for this mean square error. It's just a very nice parabola. Yeah, and if you're in a very nice parabola, even if you start from the beta somewhere here, you just need to slide down carefully to this point. And how to do this sliding down, we're going to discuss, because in these particular cases, you can do some analytical, quasi-analytical calculations, but there is serious reasons why you shouldn't do it. Because again, it's only work for linear models, and it's not applicable, for example, for the larger classes of nonlinear models where the real power of machine learning comes in. Okay, so if we're in 2 dimensions, of course, we have a 2-dimensional parabola. Yes, so we have like a bowl-shaped in general. We can draw it like this using some sort of, equipotential lines or something like that. And you can imagine that, if you have a multi-dimensional data, you have a bowl-shaped thing, or what is called the convex optimization problem. And if it's a convex optimization problem, it's a very good optimization problem because there is a mathematical guarantees that you can solve it efficiently. Okay. And as I mentioned, it's not the only choice of the loss functions. Other choice of the loss function, which is used quite often, is what is called MAI, or mean absolute error. And in this case, it's also average of the true answer minus predicted answer, but of the absolute values. Yes, so you can do a mean relative error. Yeah, so kind of like it's similar to this one, but also you summon not absolute errors, but the relative errors. Or very often what is used is a R2 score, or it's called coefficient of determination, and it's a rate of MSE divided by variance. And if R squared is 1, it's perfect, and if R squared is 0, it means that it's very bad. Yes, and of course for the MSE or Maya and relative error, of course you want the smaller the better, but the R2 score is, if it's closer to 1, the better. Sorry, and just one thing. Why by default you wanted to go to the MSE? Because as we are going to see that the efficient numerical algorithm to slide down this landscape, or also in a multiple dimension, involve calculation of the derivative. And if you calculate the derivative of the quadratic function, you are going to get linear function. But if you are going to calculate the derivative of the function like this, the problem is clearly mathematical, because the derivative of the absolute value do not exist in 0. So, and that is a mathematical challenge which one needs to encode in your algorithm. Okay, so overall, so we have a linear regression, we have a model family, yes, we have a loss function. So we want to estimate the set of coefficients, and the loss function which we are going to use, or kind of by default, is mean squared error. And how we're going to identify these betas, we're going to minimize loss function. Okay, so, and the very good or nice way to think about, and we're going to use these pictures in several in the several slides, so that we have a input data sets, yeah, and we have a family of models. It could be linear models, it could be nonlinear models, it could be support vector machines, or it could be some nonlinear regression or logistic regression and so on. This is a typical family. So our true model, because we don't know what the true model is, might lie outside of our family of existing or kind of model which we're using. And essentially, our job is to bring our approximation, which is f beta, as close as possible to the true model. And the way how we're going to measure it and how we're going to estimate kind of the size of these possible models, we're going to talk soon, and it's called the bias variance trade-off or overfitting and defitting trade-off. Okay, so now still within a family of the linear functions, let's consider the following example. So let's say, okay, I give you the linear function. You say me, okay, anybody can draw a line from the linear function. Okay, so let's take a next more complicated thing. One step up, let's take a quadratic function. Yeah, so it's a typical quadratic function to generate to us a little bit of synthetic data, and we try to fit it with a line. And of course, it's a doomed task from the beginning. Yeah, so we cannot do it good enough. Yeah, so we can try to draw a line, minimize mean squared error. We can get something like this or something like this. But the question is, can we get a better fit? And the answer, yes, we can. And the reason why we're talking to you about that, or we're giving this example, because we're going to introduce now a very interesting concept, which is called feature map. And the feature map is the additional transformation. And the idea is that all of machine learning, or a lot of machine learning, kind of even with a neural network, could be seen through this lens. It could be seen as a special family of the feature maps. But if in this particular example, we're going to choose this feature map by hand, one can see, for example, neural network as a feature map which is getting trained by the algorithms. So what is the feature map? Feature map, or just a features, is that we take our input data and we do some transformation to it. So we replace our input data. So instead of using x, we're going to use some function of x and going to feed that to our linear regression algorithm. And which feature map in this case will be useful is a feature map which is looking like this, that for every point x, it's going to make a corresponding to the x and x squared. Yeah, so it's going to turn our one-dimensional data, yes, because it's a one-dimensional data, we have a x this value, x that value, and corresponding y value into the two-dimensional data of the x and x squared. And in that case, f beta will be just beta 1x plus beta 2x squared. And now we can play the game of minimization of mean squared error, but now which is applied not to the x, but to the beta 1x plus beta 2x squared. And as you can guess, of course, you can get a perfect result. Yeah. So we can get, because we know that we generated data or kind of the good enough results from some just a y equal to the x squared line, so that we can just get this coefficient train beta such that kind of this coefficient is 0 and this coefficient is 1, and we can get a perfect fit. Yeah. So, but the important thing is that this is a very nice trick which allows you to take your data, to apply some transformation to your data, and you can step beyond the linear maps, which are very simple. And you can, if you plot your data or cuts of your data in the certain axis, you can very quickly see, are you dealing with linear maps or are you not dealing with linear maps? So could you draw a straight line through your data, or how good or how bad it is? Okay, so feature maps, yes, kind of x is called input, f of x is called features, but sometimes x is also called features. So kind of if you hear the word features in the content of machine learning, it's mean that it might be just an input data or input and transform data. Okay, so there is a zillion of feature maps. And, for example, you can have obviously polynomial feature maps. For example, if you have a two-dimensional data, you could have, linear part, quadratic part, cross product part, and so on. So you can have, exponential, logarithmic, square root, sine, cos of the data, and so on. So you could ask a free term, or it's called intercept term, which is very often used in the linear model. So it's not just y is equal to kx, it's a y is equal to kx plus b, yeah, something like that. And you can also add some other encoding of the non-real, non-numeric inputs as the inputs, yeah? So for example, if it's some sort of uh, uh, application for the rating of the, I don't know what is a restaurant or something like that. So if X is the food was good, in that case, the output should be 4. And you can design a feature map which is going to do all kind of the if X was good and it's a 4 star, so you can design some feature map which is going to assign some numbers. But I'm sure that if I look at the timetable for the yesterday and day before yesterday lectures, you've seen how to deal with this what's called the categorical data or kind of non-numeric data. So that's you can do also the feature maps for that. Okay. So now how the algorithm is formulated. So we can take some. So we have the input data, we calculate the features, and now we're just running a linear regression, not on the original data, but on the features. Yeah. So, but now there is a very nice question. Why not to throw from the start as many features as we can? Why not to go for something like this? And for example, we have a bunch of points, yes, the blue points, and we can draw, a polynomial, yeah. So we can, if it's one-dimensional data, so we can do not only quadratic fit, cubic, we can just throw in much more powers, and of course, whatever the number of points you give me, I can draw through those points a perfect polynomial, which is going to do the perfect fit. And the question is why it's a bad strategy. And it's a bad strategy because when we add in a new point, and we train on the kind of to perfectly fit the existing points, the new points do not have to correspond to our setting. And it's mean that this nice polynomial which perfectly fits blue points completely miss the red points. And humble and stupid straight line is much better fit for the blue and red points together than the whatever the fourth or probably fifth probably degree polynomial or seventh degree polynomial, something like this, because it's not could be cubic, one is going up on that, so it's a fifth or seventh degree polynomial or something like that. Yeah. So, but the question is, okay, it's clear, but and we can play this game on on this two-dimensional data, but how to do it in a little bit more systematic way? And to do it in a more systematic way, we need to take all our training data and split it into, at least now, because we'll do more later, for the two camps. One camp is called training data and another is called test data. So, and what we're going to do, we're going to use the training data to fit model, to train model, and afterwards check how the test data, which is our part of our training data, which have not been used in the training, is working. Yeah. And if we have that the training data fits perfectly, but the test data fits poorly, this is called overfitting. It means that our polynomial have a too high degree, for example, in this particular case. So we fit too good training data, but we're completely missing the train on the test data. So, and we need to find a way of doing it good enough. So this is one extreme. And another extreme is that we have our example with a quadratic function. So, and our training data is fitted poorly, yeah, but also test data is fitted poorly. And this is called underfitting. So it means that in order here, what we need to do, we need to increase the power of the polynomial. Yes, so we need to increase it to 2, for example. Yeah. So, and what we need to do here, we need to decrease. And the question is, okay, how can we play this game? And the kind of the answer will be just now. So there is a first of all there is a questions, why the overfitting happens. Yes, and there is several reasons. Yeah, so kind of the first of all, kind of like there could be so-called noise in the labels, and there also you can have what is called noise in the features. Yeah. So, and where it's coming from, first of all, that the real data could be more complex than we can capture. Yeah. Or So there might be some features which we just don't know about. Kind of like we can, I don't know, if we're studying, for example, if we want to, I don't know, predict what is, I don't know, would be the extent of the ice, as we have the example with the global warming. We can measure the extent of the ice, but there might be some other relevant parameters which we are not aware of. It could be not only average temperature on the globe and things like that, but might be something else. And that's why there will be extra noise in the labels, and also the same with the extra noise in the features or in the input data. Okay, so what is the typical strategy to play this game? So we have given our data, we're splitting it into the two groups, training and testing. And afterwards, what we do, we're running whatever our algorithm, in this particular case is the linear regression on the trained data to obtain betas. And afterwards, we can calculate what is the training loss. Yeah. And afterwards, we're calculating the test loss. The very important thing that the test data have not used in training. So training have never seen the test data. And this is a little bit more quantifiable. So L training is small, L test is large. It means that we're overfitting. L training is large, L test is large. It means that we are underfitting. And how to fix it? We need to choose right family of models, kind of just right. What does it mean? And there are various ways how you can address what is the capacity or kind of what is the right family of the model. And very typical, traditionally in machine learning, people speak about the capacity of the model, or kind of essentially, the complexity of the model, how complicated data, or what is the complexity of the model which could be captured. And the idea is that, in case of our linear regression with these polynomial features, the capacity is essentially meaning the power of polynomial. Are we doing linear fit? Are we doing quadratic fit, cubic, quartic, and so on? Yeah. So on the high capacity, more likely to overfit, as we've seen in this example, yeah, because it's probably, as I mentioned to you, the fifth or seventh order polynomial is very likely to overfit. And if it's a lower capacity, likely to underfit. Yes, because whatever we do with the linear model, it's very difficult to describe quadratic data. Okay. So how we can practically do it? Again, it's the same, and kind of it's what I mentioned to you, overfit underfit trade-off, or bias variance trade-off. So high variance is overfitting and the high bias is underfitting. Practically, what do you do? Practically, you do the following. So you start your training model, you choose your model family, for example, linear models with the linear fit, and you do the training, you find your betas, you put the training loss. So now you do, and you get your test loss. Now you increase the capacity model. You go to the quadratic model, yeah, and you get again 2 points of the training loss and test loss. You do this game iteratively. You increase slowly capacity of the model. And again, for this linear model with nonlinear features, it could be, just increasing the power of the polynomials. Yeah, for example, for the neural networks, it could be increasing the number of layers or increasing the number of neurons per layer and so on. So there is different ways to increase the capacity, as well as there are different ways to calculate the capacity of the model. But what you will see overall, that as you increase the capacity of the model, the training loss will go down. But that's why very important to also to have a test loss, because it will also, if you do things right, it will go down, 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 and afterwards it begins to grow. So what do you have here? Here you have underfitting. So your capacity of the model is not good enough to capture all kind of the peculiarities of the data. And what you have here you have overfitting, because it means that you are perfectly fitting the training data, but unseen data, which is the test data, you are fitting poor, poor, and poor. So, and where you should stop ideally, so you need to do this exercise, you need to go through these training cycles, and afterwards, you need to pick kind of just right spot. So when the test loss and training loss are both decreasing and just about to increase. So it's roughly speaking this area on this graph. So there is no hard rule how to choose it. but it's roughly somewhere here. If here would be one power of polynomial, you can choose that if we're talking about this system, but this model family, if it will be something else, you can choose, you can just try and see what performs better. But the idea is that, you try to play the game with the training and test loss, and you see how the system is behaving, and you need to pick for the stopping point somewhere here. So that would be your perfect model. Okay?
Sorry, Ilya, before you continue, there are a couple of questions on Slack.
Okay. Okay, so why it is the mean squared error squared? Why not leave without square?
No, I think
And
this one he was answered
yeah,
by the
this one is answered. Yes.
yes.
No, this is not answered. Are you answered? Or somebody answered. Okay, okay, yeah. No, because the question, of course, if you just remove the square, you have a positive and negative contribution, and you can have 1 plus minus 1 is 0. But you want it to be something like 2. What is the reason of representing outcome variable as f of x opposed to y? Is somebody answered that? Yeah, just a notation. Why is that adding irrelevant features can increase overfitting even if the model have regularization? Why is that adding irrelevant features? I mean, first of all, we haven't yet spoke about regularization first. It's still coming. And second is that, kind of like because now there's the question how to do regularization. If you do in the right regularization, and if you do the right punishments, I think, the irrelevant features should matter less and less. What parameters do we use to evaluate whether the fit was overfitting or underfitting in relationship to the data? But I think these are just answered on the picture, yes, isn't it? Where is my screen? So you just need to plot something like this and see where to stop. Yeah, so you need to plot test training loss structures, and that will tell you. Is there a limit on how much model can be debiased after it have been trained? There is kind of the limit is related to the data. It depends what is the quality of your data. Because when you're talking, but unfortunately, I don't think that we're going to talk about that at all. There is a theory, a kind of like mathematical theory of what is called the kind of like of generalization of the machine learning models, and essentially kind of like what you wanted to talk about. You wanted to estimate what is the error in your kind of machine learning algorithm performance, and usually it's coming, and I think there will be a couple of slides about that, but it's also be a little bit superficial. Um, there is an error in your machine learning performance, kind of like where this kind of training loss and test loss is coming from. It's have two components. The one component is is your data represented well enough? Do you have enough data to get the kind of intrinsic features of your model? Yes, kind of if your data large enough or representative enough. I mean, it's not even about the largeness of the data, but about representation of the data. Is your data representing enough the domain of your interest such that you could capture it? And the second is your model is good enough? So for example, as like with linear model, I can give you a lot of quadratic points, but the linear model wouldn't fit it better. There is a natural limit to how much it could fit. So, and from this perspective, that's create you a natural limit on how good your model could be made. Okay. Essentially, okay, there is one more question. How will you know that you resolve the overfitting and underfitting? Uh, you can do your best to make sure that you resolve it, but there is no guarantee because again, if it's a real data which is coming from the real experiment or real, I don't know, observation, I don't know if it's a, you can try to understand the data, or you can try to understand what exactly the model is predicting, and one can discuss that issue. But in the end, it's all so you can do your best, and you can demonstrate that you have done your best, and you need to, in principle, get your error bar, so you don't just report your trust and training loss. I'm going to show you about some extra things which one need to do, how you can try to push away the effects of the data, for example, using what is called the k-fold cross validations and things like that. But you can never be sure, because there is no perfect answer. And from this point of view, there is some formal statements about machine learning, but in the real world, you can do your best and hope that you have done right. That's what it's boiling down to. It's not calculus where there is a hard and well-defined answers. Okay, I think okay, so let me continue. Okay, so so kind of again, to determine these points, for the linear regression, increasing the feature dimension, tend to increase capacity. Again, you see tend to increase capacity, yes, and tend to decrease bias, but increase variance. So we need to construct features to balance the trade-off between the bias and variance. And again, there are some rule of thumbs. But again, kind of like in many machine learning literature, you're going to see this rule of thumbs of, how many features do you need to have as a compared to your initial feature dimension and things like that. But where all these rules are coming from, there is no well-structured mathematical proofs very often where such rules are coming from. They're coming from, especially, in the business of the neural networks, how many layers you need to take, how many neurons you need to take. Usually it's just, people have done a lot of experiment with a similar type of data, and they've seen that this rule works or that rule works. I mean, it's a lot of, experience driven things, and that's why, if you see like in many theoretical computer science research which is related to the machine learning, there will be quite a big bits which are related to the studying linear models or something which is related to linear models, because here you can do some proofs, or you can do some nice functional inequalities and things like this. But in the moment when you go to the things like neural networks, or you go to the nonlinear models, you know little nice functional inequalities from calculus or from functional analysis are not that easily applicable, or you cannot transfer them that easy. So it becomes a little bit of kind of experience based on experience. On this type of data, these things work. So you should try that and play around. Okay. So, and again, on that images, as I mentioned to you, of the models. So what does the bias variance trade-off look like? So we have our addressable family of the models. We have our perfect model, which exists somewhere where we have no idea, which also have some additional data, which might be recoverable only by additional data, which we might not have access to, or we don't know that we have that extra data, extra pieces of data. And so what is the variance? Variance is, roughly speaking, the distance between the closest to this ideal model from the boundary. Yes, so this is variance, and the bias is, how far we are from this kind of the perfect model within the class of our models to the ideal model. And the total loss is obviously sum of these two. And overfitting is when you are within your available class of models, you are very far, but it brings you closer to the ideal thing, and that's a total loss. And the underfitting is you have very small class of models which you consider. So your trained model from the kind of like this kind of f beta tilde is close, but the distance to real model is very, very far. So you essentially, you squeeze as much as you can within your family class of models, but you're still very far from the real kind of, or kind of the good enough approximation. Okay, so in an ideal, you want to be somewhere in between. So ideally, you want to be close enough within your trained model to this one, and also kind of it's close enough to the ideal function. Again, so now we're going to talk about the words which were mentioned in the questions. Now we're going to talk about regularizations. So, and the question is very easy. It's like, how are we navigating this, again, uh, bias variance trade-off of bias variance kind of landscape? And uh, what could happen and why we want to consider something different, or why we might want to kind of change our loss function is the following argument. Imagine that we have some input multidimensional data. Yes, so we have, I don't know, x1, x2, x3, x4, x5, x10. Yeah. And when we find in the beta, just by some random quirk, we could have that, one beta, for example, beta 1 is huge. And all the rest betas do not matter. And it happens like that so that we end up there in our numerical training algorithm. And in that case, what we wanted to do, and in that case, when we use the training to input a new point, the fact that, I don't know, x2, x3, x4 entries are changing on the scale of the beta 1, which is huge and which is, you kind of uh, make the kind of the entry x1 into our vector is most important, is making sure that, kind of we're getting like a skewed training. And the question is, it's not good. How we can fight it? And we can fight it with what is called regularizations. And there are several regularizations. The regularization number one, which is very standardly used, is called L2 because it's a norm 2 regularization, and which is just, we're going to ask some constant lambda plus just, sum of the squares of all the betas. So, and what does it do to our loss function? So if one of the beta, by some strange coincidence, is too high, it's going to give us a huge contribution to our loss function. So the job is now to try to decrease that kind of like, if we're going to choose some other betas, or kind of our training algorithm is going to choose some other betas, is going to make sure that the all betas are not too high. And so that, even a small changes in our input data could be affected by the loss function, or could be filled numerically in the loss function, so that we can, navigate the landscape. But what is the price for that? So that we add extra constant lambda, or what is called hyperparameter, because betas are parameters and the lambda is called hyperparameter, which means just a parameter which is essentially tweaking the parameters. Yeah, so but traditionally this is called a hyperparameter that we also need to tweak. So we need to decide how much weight we're going to give to this term. Is it will be the same weight as the mean squared error? Is it will be, a 10% of that? Is it will be 1% of that? And think like this. So what would be this lambda? Could it be 10? Could it be 1? Could it be 100? Could it be 0.01? Could it be 0.000,1, and so on and so forth. So we need to decide how to pick this lambda. And this gives us extra necessity to do the job. But before that, I think we're going to see what this parameter is doing to our landscape. Okay, so first of all, why L2 is useful, or what is the intuition behind regularization? It's encouraging simpler functions, because, if the lambda is very high, so in order to minimize it, betas will need to go very small. So what lambda is used for, it's used for exactly tuning this bias variance trade-off. Okay, so now how we can represent it graphically. So we have our, let's say, two-dimensional data, just for the clearness. We have our mean squared error landscape is this red ellipses. Yeah. So sum of the beta squares is a bunch of circles which are centered in the beta. Yeah. So we have a green circles, and what we're doing when we are calculating our loss function, we're adding a contribution from here in the beta space and the contribution from here from the red ellipses. And sorry, Tutukili, can you see my mouse moving?
Yes, yes, I can.
Oh, okay, just in case, no, because I'm doing some gestures with the mouse and I was not sure whether anybody could see it or not. Okay, so and essentially what we need to pick when we're minimizing our loss function, where we need to be exactly in the right spot or good enough spot, which is minimizing both of these contributions. So yeah, if lambda is 0, of course we're going back to our standard bottom of the convex ball, yeah, of the kind of like our parabola. And if the lambda is infinity, we are in the beta is equal to 0 because we're sitting somewhere here. So our job is to get into the good enough point. Yes, and of course the goodness enough, we need to be somewhere here. Yes, we're also determined by the size of the lambda. Okay? So also there is a little comment if we have this intercept term. Usually one is not adding the penalty on that because we're still anyway we're training that beta 1. So in that case, but that's a little irrelevant thing for us because it's just usually implemented on the level of the software for us. Okay, so why also it's a very interesting and useful exercise to add regularization because of this very simple observation related to the linear models. So if we change the scale of the features, instead of x or every entry xij, yes, kind of like in the vector 1, all the ij entries we are going to increase twice. In that case, without regularization, if we just half all the betas, we'll get the same solution. But that sounds a little bit odd. Yes, so kind of like that gives us a little bit of non-uniqueness. But if we have a regularization term, if we play the game with the change in scale of the x's, what are we going to get? That our penalty is going to be changed. And this is also a reason why we want, maybe we want to do something to our features or to our input x's, but in such a way so that we can have some sort of universality in our training. And typically what is done is feature rescaling to the kind of like quasi-normal distribution. Yeah. So kind of what does it mean? So we calculate what is the mean of each features. Yes, kind of like what is the mean value of every, I don't know, first entry in each vector? What is the variance? And we just divide it, and we just doing xi minus mean divided by the variance. So we're bringing to the kind of a normal value in the each or kind of Gaussian distributed random variable from the each entry. And afterwards, we apply a learning algorithm. And also one of the reasons why you want to do that is if your data is allowing that, because the most of the proofs for the guarantees are usually done for the randomly distributed Gaussian variables. So kind of like it's also help or give you extra guarantees mathematically. But there are also different feature standardizations. So this is one of the standardization which is related to kind of to bring to the normal distribution. But there are other ways, like there is a min-max standardization and several others. But within the package, within the tutorial part, I will mention the package as a part of the scikit-learn, which we are going to use. There is a whole bunch of different standardizations. Okay, so now what we have, so kind of we need what problem we need to solve. We need to have our original loss, yes, when we're minimizing betas, but also we have our regularization term, yeah. And now we not only need to find betas, now we need to also identify good enough lambda, which can help us to solve this problem. And minimizing, now we're minimizing not this red mean square error, but we're minimizing this sum. Okay, so what do we need to do? In theory, so what do we need to do? Yeah, we need to try different values of lambda and choose that which is minimizing the test set. And the problem is that we might end up with overfitting. So, and now the question is how we can systematically do that. And systematically done that, again, in a splitting more data. So now we're coming to the usually there is no more splits, so kind of people don't assume more splits by default. So what we do is a given data. We're going to pick a biggest piece to the training data, smaller piece for the validation data, and one more piece for the test data. And for all our shenanigans with training, we're only going to use training and validation data. And the test data is only going to use for evaluation, but never for training. Because if you use any bits of the test data for training, you're going to give prior information to the model about your test data, and you're going to deal with the issue, which is called contamination of the data. Okay, so how our strategy is looking like. Now, what we do, so we say how many times we wanted to, kind of how many different lambdas we want to essentially to evaluate. So we're running a linear regression on the trained data for a given lambda. We calculate betas, and we evaluate using the validation data for a given lambda. And afterwards, what we do, using that, we find what is the best lambda for the given training data. And okay, and kind of like this is a procedure, but what sometimes can happen, and that is happening quite often. So when you do these splits, your data might be just by random shuffling is not be good enough or well enough represented. And what you might measure the performance of the model. You always measure the model plus data, but what you want to separate and minimize data contribution. And so what the people do is so-called cross-validation. So essentially you take your training data, validation data, and test data, you play the game, and afterwards you use for training the different parts, and you use kind of another part of validation data, but you never touch the test data. Test data you cut off and put aside and don't touch. And you do this, different parts. What does it give you? And kind of like based on that, you can get your sets of betas and lambdas, and you just can just compare them to each other and see are they similar. And if they're very different from each other, it's mean that you're doing something wrong. But if they're close to each other, you can take an average, or you can use it for the mean and deviation of your test results and so on. But the idea is that by doing this exercise, and by rerunning the algorithm multiple times, but on the different splits between the training and validation data, what we're trying to make sure that the training of our model is kind of what the performance which we're reporting is really performance of the model, and kind of minimize the influence of data. And we can formally formulate it as a kind of algorithm, and within the scikit-learn, and but also within all the standard machine learning packages, we don't need to worry that we need to implement it manually. Of course, one can implement it manually, but within the standard machine learning package, it is implemented for you, and you just need to use the corresponding function. Okay, so you don't need to use the threefold cross-validation. You can use the, I don't know, fivefold, tenfold cross-validation. It just depends on the data which you have. Yes, so we're split into the training and test data, and train data we split into the train and validation with the different subsets. We play the game on the train and validation to find the beta lambdas, and afterwards we use the test data to report results. The problem, of course, the more splits you have, the better quality becomes. But of course, the more times, because in this threefold cross validation, we need to do the same job 3 times. Yeah, training algorithms, evaluate, find the hyperparameter, and evaluate on the test data. Yeah, so we need to do it 3 times. If you have a fivefold cross validation, you need to do it 5 times. 10 cross validation, 10 times. 100-time cross-validation, you need to do it 100 times. And of course, it's more and more computationally expensive. So, and usually you need to find the compromise. And I think usually, for the large enough data set, 5 or 10-fold cross-validation work good enough. Okay, so where we are. Okay, so do we have any questions? Because we're
Yes, we
Mhm.
have some
ah,
questions, and
okay.
yes, and also it's 5 minutes before our tea
Yeah, yeah,
break.
yeah.
Yeah.
But that's what I was looking at. Okay, so why is beta zero not included in the sum L2 regularization? Okay. Okay, so let's go to that slide very quickly. Is it this? No. Have I jumped over where it was? Sorry, guys. No, here the original. Okay. So why it's not included? The question is because what does this term one is doing? We are not multiplying it by any entry. So why do we want to play this game with the regularization? We want to play the game with the regularization to make sure that we have a good sensitivity to change in the input data. But there is no change in the input data. It's always one. Does it answer your question? Because why do we want to play with the kind of why we want to punish some values of betas? Because if you have, I don't know, beta 1 and beta 2, or kind of, I don't know, and the x1 and x2. So your problem would be, okay, so you're happy. Okay, good. Okay, what is the percentage for each subset of the data train validation test? Okay, there are some typical guidelines, but it strongly depends how much data you have. Because if you have a little data, here they suggest rule of thumb against 60, 20, 20. You could do 70, 15, 15. It's you just try and see. It depends how much data you have. If you have 100 points at all, all your data is 100 points. Maybe 60, 20, 20 is a little bit too much, and you want to do 80, 10, 10, and things like that. But you just do experiments and you see how it's performed. But that's why also the nice thing is that you wanted to have not just you train a model and forget about it, but you want to have some real life outcome. For example, if it's I don't know, some experimental setup, you try and see is 80 10 10 split works good enough or not. Yeah, yeah, it's a correct answer. You can decide, but you just need to see does it work on, oh, it does not work. But the typical answer is 60 20 20, but it's not again, machine learning is not about, there is no hard rules, because it's really experience a gut feeling and many many experiments. Okay, so there is no more question. I think that we can probably stop here, because afterwards there will be L1 regularization, and I don't think that I need to start. What do you think, Tutukile? Yeah, because
Yes, I think we can stop here and have our break and resume at 11:15.
okay, wonderful.
Yeah.
Okay, is everybody back?
Yes, I think we can resume.
Yes. Okay. And I think it's a little bit calm down on this side, so I think that I could have a camera on for a little while. Okay, so what we finish with you with this k-fold cross-validation, and as we were discussing, we need that procedure in order to know kind of like that we want to eliminate as much as possible the effect of data from our results, so kind of or random distributions in the data. Yeah. So there is one more problem which one want to consider is that, if you imagine that you have a lot of input features, kind of like, if your input vector have a lot of entries, and you don't know which are relevant and which are not relevant. And now using L2 regularization, we can make sure that they're all roughly speaking on the same scale. But now some of them might be irrelevant or very small. And what we want also, we want to have, because what we're supposed to do for machine learning, I mean, we're supposed to create a model, train the model, do the predictions, see how the prediction work. But I mean, that's not good enough. What we need to do afterwards, we need to understand what exactly is driving the model's performance. And that's one of the problems with the neural networks. We need to be able to interpret the model, what the model have learned. Because otherwise, what we have learned that there is a black box which is spitting out to us numbers, and what? There is no. It's okay. Sometimes it could be useful if it's not a critical thing, but if you use machine learning as a system for doing something critical for research or for society or whatever, it would be very good to understand why machine learning have predicted certain values, or kind of why have done certain predictions and they work well. There should be at least some model of what's going on. And in order to do that, what would be good is it would be good to say that the smaller betas are relevant for the system, the better. And that's give us ideas of some sort of L0 regularization, which is just give you what is the number of or sparsity, what is the number of non-zero entries out of those betas. And of course, kind of like when the beta size getting smaller and smaller, it's mean that it's mean that if for example beta 10 is very small, it's mean that this x10 input in your vector of the input data is really irrelevant. For example, as a physicist, I can give you example from physics. If we're trying to build a model, of describing, what's happening when we drop things, if you could see on video, I just drop a little marker. Yes. What is relevant parameters? Is it relevant that the marker is a black marker? For example, and in principle, when we do the input data and have done the experimental observation, we're supposed to input all possible features of the data. And the machine learning algorithm should tell us, oh, the fact that it's a black marker is completely irrelevant. And in this particular case, because we know the physics of the falling bodies, the only relevant feature is what is the mass of this thing and what is the height from which it's falling. Kind of like, but that's kind of what sparsity kind of as a regularization should tell us that okay, so we want as little betas as possible which matter, so that the all irrelevant betas are just zeroed out. Okay, but the problem is that kind of the function like this is not differentiable, and it's very hard to optimize. And the partial solution for this thing, because is use a not L0 norm, which is just counting zero and non-zero entries, use L1 norm, which is just an absolute values, which is also not really differentiable, but I mean, at least it's not differentiable in some points, not everywhere. So, and from this perspective, it's a little bit better. It's still hard to optimize, but at least it's a convex problem, that at least one can play this game. So, and how practical it looks like, this L1 regularization, if we just, instead of summing beta squares, we're just summing just absolute values of beta, instead of circles, we are getting these kind of squares, yeah, and in the multiple dimensions will be multiple dimensional squares, if you can imagine them, yeah. And in that case, yes, when this hyperparameter lambda is very large, we're sitting here. When it's very small, we're sitting here. And when we do the optimization, we are somewhere kind of we're trying to maintain balance between this regularization and this regularization. And of course, you can also add beta squared. What is the advantage of this regularization compared to beta squared? Because when the beta squared is just pushing your value of beta stronger. So when you don't want to push it too strong up, or you don't want your beta's persecution to be too large. So because when you do the squaring, you obviously the higher polynomial growth. Okay, so this is kind of okay. So this is the logic behind this L1 regularization. And again, we don't need to know how to implement it because within a scikit-learn, it's implemented in a standard way. Okay. Oops. Okay, so you can use L1 regularization for so-called feature selection. Yes, so we can construct a lot of features, add them to the feature map. So we can add a lot of transformations, random transformations and so on. And afterwards, we can use L1 regularization to select the features which are kind of interesting and good enough, and leave them, and all the rest we can take away. Okay, so now the question is that I told that, oh, we need to minimize the loss, yeah? So this loss or MSE loss, we need to minimize it. But I never told you how. Yeah, and I told you that in case of the linear models, whatever the loss function is, we have a kind of mechanism which could be dealt quasi-analytically, but in fact it's not very useful. I'm now going to quickly overview what's happening that you can do it kind of quasi-analytically, and this is used again. The researchers are using this semi-analytical form because you're producing some large expression, if you want to do some analytical bounds. But again, it all works only in the linear case. When you go to the nonlinear case, unfortunately, these nice analytical formulas are not applicable. And what you need to use some numerical mechanisms to kind of the wander the landscape of your loss function. And in case of the linear models, the landscape is convex, so it's a very nice landscape to wander around. Or it's kind of, and there are mathematical guarantees that you will, if you do things right, you will reach the so-called the global minima. So you will reach that the point of optimality. But if you're talking about, the loss landscape for the more complicated nonlinear models, which wouldn't be convex, which means that they're not bowl-shaped, from practical point of view, that they could have certain minima, what could happen to you, that you can just get stuck into those, and people develop special methods how you can try to avoid those places as well. Okay, so we need to minimize this, and there is two standard approaches. One is a closed form solution, which I'm now going to revise quickly. And more important, it's a numerical search, which is called optimization-based solution. And I'm going to present to you the simplest version of it, which is called gradient descent. But there is also gradient descent and even non-gradient descent based method to solve the same problem. And as the parts of all the standard packages, for example, for the neural network training and so on, all these optimizers are built in, and this is your another hyperparameter which you will play with. So you can use, I don't know, gradient descent, you can use stochastic gradient descent, add them, and blah, 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 Nesterov, and so on. Okay, so let's go into the quasi-analytical form, and just it's a vanilla linear regression. So if we now write it in the matrix form, so for the entry of the vector 1, we put into the first entry of this super vector, yeah, f beta of x1, f beta of x2, so it's our n predicted outputs and the n labels, yeah. So, but in fact, each of those guys is the beta t on x as a vector, yeah. So it means that it's a beta 1 on x11, beta 2 on x12, beta 3 on x13, and so on, yeah. So it means that we can write it like this, and it means that we can in turn represent it as the matrix where this is our input data as the rows, and kind of like each column is a separate entry in your input data, entry number 1, entry number 2, entry number d. Yes, and it's multiplied by beta to be like a matrix vector multiplication from this side. So, and in summary, we need to solve equation like this. Y is approximately x beta. Okay, and we need to find beta. okay, we need to find which beta which satisfy or which minimizing mean squared error. So how we can rewrite a mean squared error? Mean squared error is, yi minus beta xi squared and sum of those. So it's mean we can rewrite this as something like this, as the vector minus this vector, which is x beta, and the fact that we are summing up squares, it means that we're just doing standard Euclidean or Pythagorean square, yeah? So just y minus x beta, this vector minus this vector, and we're just calculating the length of this vector, okay? And, we need to find the minimum. How we find the minimum of multidimensional function? We need to, how we find the minimum or extremum of the one-dimensional function in your standard calculus, and, most of the students in the natural sciences have a first-year calculus. We need to find the points of extremums, and that you find it by find the derivative of the function and to equating it to zero. Yeah, so in the multidimensional case, you do the same thing. We need to find the extremal points, means that we need to find, and afterwards we need to check that, that point is point of minima, not the point of maxima. And this you do with the second derivative, but because for the linear function, we know that it's going to be, there is no point of maxima, it's only point of minima, so just find the zero is good enough. And in multidimensional case, we need to take a gradient, or roughly speaking, we need to find the derivative with respect to every variable, to every beta, out of this function. So we can do it formally. Yeah, so we can find the gradient or derivative in each beta out of this expression, and it will look like this. Okay? So, and now we need to set it to zero, and this equation will determine to us the sets of betas which are optimizing exactly the point of minima on the bottom of the ball. Okay? So we can write it like this. And what do we need to do? We just need to apply the inverse of this matrix, and this matrix will be invertible because it's at least, this matrix will be squared. So at least we can write an inverse or pseudo inverse to this matrix. Okay. So, and this is, under assumption that the x is invertible, but, that doesn't misspoke because I know that it's not always the case. And we're going to have a simple examples when it's not always the case, but, and we can write the expression. One can play the same game with the regularizers. We can add regularizers and get the same quasi expression. But the problem is that, when we have some real input data, we could get a situation when the matrix is not invertible. For example, the very stupid case is looking like this. So when this matrix xtx is this 1, 1, 2, 2. Yeah, so it's a matrix with a zero determinant, and this matrix is not invertible. But this system is still solvable. This system is solvable beta 2 is equal to 2 minus beta 1. So, and the question is, how we need to treat this situation. And, and when you have a huge matrices with a lot of entries, you are always going to have, or very likely going to have problems like that. Okay? So, in principle, one can write it down. In practice, it's a very nice formula if I want to prove some, mathematical bounds. In reality, sometimes, first of all, calculation of the inverse matrices could be difficult, computationally difficult. It grows as the cube of, the complexity is growing as the cube of dimension. So if you have a 10,000 features, so if our input data is 10,000 input features, so it means that we need, our complexity is growing as 10 to the 12. It just will be very, it will take a very long time, roughly speaking. And if the matrix is not, and this is based on if it's invertible, but if it's like this, but on the larger scale, we cannot invert it. Yes, so now we need to play some tricks, and it's getting more and more difficult. And what for? To solve linear models, which is the simplest model which you have, and which are not always capturing the all the kind of the hidden relationship between the points. So it's far not the optimal way of doing it in the real world. And in the real world, what you want to do, you want to do it using optimization route. Yeah, and this strategy in the simplest case is called gradient descent. So, and what is the basic idea of this approach? The basic idea of this approach that we just need to initialize betas randomly, and afterwards go into the direction of decreasing of the function. So essentially, where is our image? So we initialize at random points, somewhere here, for example. And afterwards, we need to do something so that we, with every step, we just sliding down into the valley until we reach minima, and we're stuck there. And when we see that we are stuck there, okay, so we, in the case of linear model, because it's always a shape like this, but it could be multidimensional. We guarantee that if we go into the direction of the minimization of the function of the minimum growth, we will go into to hit the point of minimum. So how do we know in which direction to go? And that's again that good old gradient. Because what is the mathematical meaning of the gradient? Gradient is showing you direction into the growth of the function. It will give you a vector in the direction of the growth of the function. So it means that if you want to go to the direction of the minimum decline of the function, you need to go opposite direction. Yeah. So, and that's exactly what you do. That's your update rule for the parameters beta. So you have on the step t, you have a beta, and now you are moving this vector of betas into the direction opposite to the direction of maximal growth with some speed, which is called learning rate. And this is another hyperparameter like lambda in regularization, which we will need to play around and optimize. Okay. And in the real world, not only linear models, but so in the neural network, and with the neural networks, you can go and Google images and type neural network loss landscape, and you will see images which are looking much more strangely kind of much more spiky than this one. So kind of it's a real problem how you go in this loss landscape. But for example, here we have a few hills. You can randomly start here, and afterwards, as you go through your uh, gradient descent steps, you can, for example, get into here, but even on this picture, it's seen that, this minima is lower than that minima, so that you can stuck here and never get into the here. And this is a big problem, how you navigate it, and there are various ways of navigating it. And, when we're talking about the linear models, we are not going to have this situation. We're always going to be inside of the ball. But when we're going to the systems like the kind of the more complicated non-linear models, we can get here, and the ways how get around is you do it many times, and you see where you end up, and you reinitialize from the different points of this energy landscape. And if you more often end up here, that's probably is your better point. Or if the loss function is smaller here, that of course it's help you identify the points. Yeah, so kind of like that's where you want to go, but you can easily, as a function, where you start, are you starting from this side of the hill or this side of the hill? So it's mean that it's not once operation. So usually you need to do it several times. So you need to apply some methods when the software is doing it for you, so that it's reinitialize it in some nice way, so that it can go, so you can tap different paths on the loss landscape. Okay, yes, for the linear case, it's so simple, because wherever we start, we are always going to end up in the global minima, because this is, by the way, this point is called local minima, and this is a real problem. That's where you can get stuck in your optimization. You can stuck in some local minima, and in that case, you need to see what can you do with that. And this is a big problem in the practical optimization. Okay, so what do we do with the gradient descent? We initialize some values of beta. And again, how to initialize, that's a separate business. So again, people have done experiments, and they find that, for example, for neural networks, this type of initialization works. For this system, that types of initialization works. So it's again of kind of like set of experience accumulated, and which one just need to try and see. So and we do the loop, yeah, of the, where is my loop like this, until the difference between this vector and this vector is smaller than some error rate which we define in advance, for example 10 to the minus 10. So when these two vectors are so similar, we say that okay, we are already in the point of minimum. Okay, so you can initialize it in 0 and, for example, repeat until convergence. But again, what the convergence is that the difference between the two successive steps are not too large. Okay, so for the linear regression, of course, we get in points until we get into here. What does it mean practically, the word convergence, it means that, the difference between the two successive steps is smaller than some well-defined epsilon. So you need to choose some epsilon, you need to choose what is your sensitivity, what is your threshold. And you play this game. Okay, so now a little bit of intuition behind the learning rate, because we get one more parameter to play with. We have that lambda in the regularization, or we might have two lambdas, L1 and L2 regularization lambdas, but now we get a learning rate. What is the learning rate and why it's important to choose the right learning rate? Because if it's very small, what happens? That the loss is decreasing too slowly because you're just making too small steps. Yeah. But if it's very large, you're just jumping, and you can even get out of your minima. So it means that in practice it needs to be not too large but also not too small, and you need to be somewhere in between. And there are different ways how you do it, and there are different strategies. For example, there is a typical game which people are playing in this part of the business is they start with a little bit larger learning rate, but they also do what is called the schedule of the learning rate, so that as you make certain number of steps, the learning rate, you begin to decrease it, and you can again decrease it constantly, or you can decrease it like in the steps, 10 steps this learning rate, 10 steps that learning rate, but again, you do experiments and you see what's happening, because that's the only way of training machine learning algorithms. Train, do experiments and analyze and change one variable at a time. Okay, so the choice of the learning rate, yes, it's based on our training data. If it's too small, the loss is decreasing slowly, too large, loss increasing. And one first can try the different learning rates and see what's working. But again, as I mentioned, within the modern machine learning packages, TensorFlow, PyTorch for the neural networks, you can not only choose the fixed learning rate, but you can also choose the so-called the schedule of the learning rate. So which is just, it's telling you how the learning rate is going to be decreased, because obviously you want to start here with a larger learning rate, yeah? But you want, as you get in closer, you want to start to decrease in learning rate so that you there's nothing too wrong with the small learning rate, but you want the small learning rate here. And here you want maybe not that large, but large enough learning rate so that you do the big jumps here. But as you get here, you have a smaller. Here you have very small learning rate, because it's also, if a very small learning rate give you an even more smaller change, it means that you're convergent, you're good. So you can say that, okay, I have minimized my parameters. Okay, so we can compare strategies, but as I mentioned to you, like in the case of linear models, you can have both strategies, but it's only in case of linear models. In the moment when you go for some other non-linear models, there's only one strategy, is doing optimization numerically. Okay, so for closed form solution, we don't have a hyperparameters, but you can get a kind of computational difficulties for the large enough data with a large number of features. So with the gradient descent, the price is that we need to play with alpha. So we need to play with the learning rate and also the scaling. Okay. And yes, kind of like, as I mentioned, the gradient descent is very basic and standard algorithm. So there are people already develop more efficient algorithms, because again, in some sense, gradient is defining you kind of like your speed, how you move in your land landscape. But you can also vary what is called acceleration. Yes, you can vary derivative of the of your gradient, and for example that kind of like Nestor momentum type of optimizers and things like that. So you just need to play with them and see which works better for your problem. Okay, so let's do some recalls, and kind of I think we're coming to the wrapping up of this part. Yes, so we have L2 regularization. Yeah, so we can calculate the gradient again here. And if we can calculate it in a quasi-closed form, and we can also get, some expression, and essentially what this lambda is helping us to do in this case, it's helping us to make this matrix XTX invertible. Because this is also a very, very useful piece of information, because that's, numerically we can find the non-invertibility of the matrix using the regularization. but we cannot find, the complexity of or computational cost. The fact that, and this is a generic trick, if you do some numerical calculation for something else and you suddenly encounter non-invertible metrics, this is one of the things which people do. They just add in a small parameter on identity matrix, and this matrix is becoming automatically invertible, and you just play with that small parameter and you try to identify the limit of the inverse of the matrix as that small parameter is decreasing. So at least that's a kind of tactics which people use as a regularization, not only in machine learning, but also just in solving, linear systems and things like that as a part of your standard, whatever numerical routine. Okay, so we can play the same game with the gradient descent. So, and what this term is doing to us for what the regularization term is doing to us in the gradient descent algorithm. So this is our term which is coming from the algorithm, but this is term which is we can interpret it as kind of weight decay, which encourages betas to be small. Okay, so that's about, I think, linear models, and I think we are now going to jump into the, if I'm not mistaken, to the classification tasks. Okay, yeah. Okay, so very quickly, just to wrap it up. So we have our data. So what we want now, we want to find the betas such that we are minimizing the loss, which are kind of this, our model is solving approximately y is equal to f of beta of xi. And, after the training, and it could be not xi, but phi of xi features, yes, we're getting our model. Yeah. So the label here, a bunch of real values. Yeah. So the another task which I mentioned to you, which is very prominent and very important, is what is called classification. And it looks very, very similar, but now what the y's are, they're not just because for the regression, y's are or labels are any real number. Here, it's a bunch of discrete numbers. Yeah, it could be 0, 1 if it's a binary classification, or it could be 0, 1, 2, 3, 4, k if we have or k minus 1 if we have a k classes. If we start from 0, or if we started from 1, it will be k classes. Yes, as I mentioned to you, ImageNet, the typical data set of the bunch of images, which I think in the standard form have 1,000 classes. So in that case, classes are from 1 to 1,000, or because it's a new kind of numerical in Python, it will be from 0 to 999. Okay. And as we've seen in the beginning, yes, kind of like what is the typical task for the classification, for example, for the binary classification, but also there will be similar story for the multi-class classification when we have more than 2 classes, is that we have an input data set which have, some bunch of features plus label, class 0, class 1. Or in this case, in this example, is it malignant or benign ocular tumor? Because this is a retina shots and, and supposedly, the patients have a tumor and you want to know, is it tumor? Did this tumor need to be treated now, or it could wait a little bit and one can do a little bit more observations. And essentially, we could have, for example, if we have two features, tumor size and the age, and if we have benign tumors and malignant tumors, what we could see that they essentially everything which is line, we can draw imaginary line, which is called the decision boundary, which is saying that, if you are below decision boundary, you are in this class, you are in the benign tumor class. And if you're above this line, you are in malignant tumor class, or at least, kind of like, and it's not necessarily need to be a straight line. It could be, a little bit more wiggly line, but essentially the idea of the classification task is to construct within your data these decision boundaries. And if you're dealing with a multidimensional data, you could have a more tricky cuts in your data, saying everybody who sits in this corner is belonging to this class, everybody who sits in that corner is that class. But the job is to draw the boundary. Okay. And now, that's another example. Yes, so kind of we have a data set. So we have a label 0 and 1 for the binary classification as the simplest one. And we need to predict that we are in the class 1, for example, if we have some parameter x beta on xi's are greater than 0 and class 0 otherwise. And the job is that now we could try to play the game which was similar to the linear regression, but we need to change something. First of all, we need to introduce a loss function. Yeah, so because we need to say how we're going to judge whether our algorithm in this case, because we're not spitting out just values, the only thing which algorithm is supposed to spit to us is 0 and 1. And how to measure now the goodness of this algorithm, that's what we need to know. And for that, we need to find how the loss function will look like. Okay, so you can have a different loss functions which are based on again, like in the case of regression, we have the MSE, Maya, and there are R2, and there are several others. But what we can do, we can base it on the distance, because we have one class of the red dots and the blue dots. We could draw the boundary, and now we can see, okay, now we can try to classify how are we misclassifying, or we characterize how we're misclassifying, meaning that, okay, so now we need to say that, okay, that this red dot is more misclassified than this red dot. Why? Because this red dot is closer to the boundary than that red dot. They're both misclassified. So they really need to go into the kind of like loss function or punishment function, in sense like, the punish the algorithm which is giving you this decision boundary. But now, we can try doing the distance-wise, and kind of like this could be one of the approaches. But in that case, now we need to define a distance, and that's the next question to think about. And if loss function is zeros, it means that we are reaching 100% accuracy. And for some algorithms, it's possible to achieve. And generally the family of the algorithm which is dealing with the distances is called support vector machines, and it's just one of the algorithms. And I think I might be talking about that maybe tomorrow or maybe later today. I don't remember, if to be honest. But one can consider something more generally, kind of like when we cannot introduce the notion of the distance, what are we going to do, or how we're going to do it? Okay, so, and in order to do that, we need to change our lens on the machine learning. And machine learning could be seen for the several perspectives. So, and kind of it will give us one absolutely the same results, but you could have a different perspectives, and you use these perspectives as the function of your convenience. And the perspective which I want you to tell 2 words about now is probabilistic perspective. So essentially, what we are now going to deal with, or how we're going to view on on machine learning task, is not on kind of we're estimating model which is giving us prediction. What the machine learning task is to give us out the probability distribution, which is the best probability distribution to describe our data. And if some of you have a physics background or heard the course of statistical mechanics, you can really think of that it's a change of ensembles in the statistical mechanics. For example, in a canonical ensemble, when you fix the temperature, energy becomes probabilistic variable. But of course, the energy is well defined, because the probability that the energy takes the most probable value is extremely high. So essentially, all the deviations at room temperature for the gas in this room is unobservable, but it's still, formally speaking, a probabilistic variable. But in the same way here, so what does it mean? That you have a well-trained linear model. So when you well-trained linear model, your probability distribution is describing exactly the probability distribution which corresponds to the linear regression. Okay, so, and in order to do these estimations, how we can estimate which models is given to us, which probability distribution, we need to talk about the likelihood estimation. So kind of like, what is the likelihood that this data could come from this probability distribution? So we need to clarify this in some way. And we have this strange notation of IID, but it's like independently. Essentially, it's independent points. IID. Oh God, what is the IID? Who can tell me what is the IID? So sorry. First of all, there is a question. Independent and identically distributed. Yes, identically. I forget. Yes. Essentially, it's independent. It's a bunch of independent points which we can treat as not related to each other. Okay. What if there are local minima that not quite the lowest? When What if there are local minima that are not quite the lowest? Yes, I mean that's a local minima which is not the lowest. No, but you just do more and more experiments, and if you sample enough from your large enough space, you're supposed to get there if you're lucky. There is no guarantees. Okay, so let's go to our random points, and essentially what is the maximum likelihood is going to give us? It's going to give us a probability that what is the probability so that the given x we're getting the given y. Okay, so and this probability distribution define as model family. Okay, so now kind of like what is the kind of the difference and the similarity to what we have before? So before we were saying kind of how can we characterize that y is approximately our function, linear regression or whatever. Now we're saying what is the probability of obtaining y given the input x. But as we're going to see, it's a very close ideas, and it's just the same view on the same instance. Yes, kind of the intuition is just this f of beta, or our kind of like linear model, provide us with the point of y, and the probability distribution provide us also a score for the possible points. Okay? So a maximum likelihood estimation combine the loss function and the model family in some sense. Okay? So how now we're going to do it? So if we have an input of our inputs on our outputs, because they're independent, the probability that given the inputs we get the outputs for the given values of beta, because each input is independent, it's just a product of the probabilities. Yeah. So and now if we try to minimize something like this, it's rather mathematically challenging because if you're multiplying a lot of small numbers, you're getting an even smaller number. If you're multiplying a lot of numbers, which for example is greater than 1, okay, probabilities could not be greater than 1, but you're getting a very large number. Yeah. But the idea is like if you minimize the product, it's not good. So, but there is a standard operation how we can take a product and bring it into the sum. We just need to take a log. Yeah, so if we take a log of this, we're going to get a sum of the logs of each entry, and it kind of we have log likelihood. And now, why we need to take it negative? Any suggestions why we would like to take minus? Why it's negative log likelihood? Why it's not positive log likelihood? So what will happen, if I have a given xi and I'm getting exactly the correct yi, what would be the probability? Or if I get an a wrong yi, what would be how these two probabilities will compare to each other? So if I'm getting the right yi, my probability will be higher. Yeah. Or if that yi which I'm getting randomly from the probability distribution, if I'm getting closer to the right yi, it's going to be higher. If it's going to be, at least that's what I want from my likelihood estimation. If it's a yi which is far away from correct yi, I want it to be that probability to be lower. Yes, so kind of like we'll get that in the process of choosing betas or training for betas, our probability needs to increase. Yeah, and we have kind of increasing here. Log is the function which what does the log do? How the log is looking like? Yes. Good. Yeah, because we want to still to do the minimization game essentially. We can maximize log likelihood or minimize negative log likelihood because log is behaving like this. So it's mean that if we want to increase probabilities and it's also log, it's also increasing function. So we'll get that overall the function will grow, but we want to, because we have the language of minimization. That's why we have a sign minus, and now we need to minimize this growth, which will of course correspond to the maximization of corresponding probabilities. Okay, so and the intuition behind the likelihood is to say that high likelihood or the high likelihood, if we have this is our problem, if we have a bunch of points here and bunch of points there, curve line like this is much more likely than the line like this. So that's what we want from our likelihood function. And now the question is how to construct it. And the easiest way to construct it, for example, for the linear regression, we know that we need to increase the share or kind of the probability for the fact when the y is closer to beta xi or beta xi is closer to y. How we can do it? We can just, if we do something like this, so if we assume the Gaussian probability distribution, yeah, so kind of which have a minimum where this is minimized, we are going to have a maximum probability there. So the very nice conditional density for the linear regression is looking like this. Yeah. And now let's see what happens with our negative log likelihood. So if this is our likelihood function, negative log likelihood or minus log of this is exactly mean squared error. Yeah. So because this will be a constant, which you can forget, because we're going to take a gradient from this, yeah, and the gradient from the constant is 0. So gradient from this will exactly give us absolutely the same results up to the constant, yes, because MSC was factor 1 over n, but this is a constant factor which one can add. And that's why describing a linear regression on this language or on this language and on the language of just explicitly on the functional language, if you do things right, will give you the same result, because it's just a different view of the same things. And this kind of the idea that the machine learning algorithm is giving you a probability distribution of your, which is consistent with your input data, is a very useful concept, which is not only used in the classical machine learning, or you can move it to the deep learning, because what is the deep neural nets? It's essentially probability samplers, and these probability samplers could be used for the different purposes, including the computational purposes in the condensed metaphysics and so on. But this idea is also very naturally gets transferred to, for example, to the quantum machine learning or to the quantum physics domain. So what is a quantum machine learning algorithm? It's just a specific probability sampler. So that's why, it's a little bit more difficult to conceptualize, but the idea is essentially kind of for the classical machine learning algorithms, it's worked absolutely the same. It's just the different views. And sometimes for the certain classes of analytical proofs, when you move your machine learning problem into the probability theory, what you're ending up with that the fact that now you can use all the machinery of the classical probability theory in order to apply to your machine learning algorithms, which also could be useful. Which allows you, for example, to take into account naturally the finiteness of the data or incompleteness in the data and so on and so forth. Okay, so which means, kind of, because this probability distribution make exactly negative log likelihood essentially the same loss function as the linear regression, that MSE. So we have the same problem. We have a minimization now. So if we have this probabilistic approach, we have the minimization now for this negative log likelihood. But this gives us just a blueprint of how we can approach the problem, for example, of classification. Because why we're talking about that we need to have something, we need to have some loss function or approach with the loss functions, but to the classification problems. And yeah, so kind of, again, this will recover the linear regression, but now we will jump into the classification problems. Okay, so maximum likelihoods from the view of machine learning. So we have a decisions which we need to take. We need to choose the likelihood function, and we need to choose optimizer. Yeah. And in the same way, so kind of like to the things which I told you before, we need to choose the model family. So, and again, we need to choose the optimizer. So kind of like it's the same game and it's equivalent, but it's very useful to jump around between two. Okay, so but now what can we do with our classification tasks? Okay, with our classification tasks, we also need to introduce some form of probability. And essentially, we can introduce many kind of conditional probabilities, but there are some conditional probabilities which works better than others. So, and if we're going to say that, that the probability that, that the input xi correspond to the class 0 is behaving like some negative exponent of beta xi, it means that the probability of the class 1 is behaving as a positive exponent with some coefficients of proportionality. In fact, this naive choice could lead us to the very interesting results, because if we know that the probability of the class 0 is behaving like this, probability of the class 1 is behaving like this, or proportional to like this, we can calculate the coefficient of proportionality, and this coefficient of proportionality will look like this. For example, for the class 1, yeah, we just need to sum it up, and you just imagine that you have here some coefficient C here, and you can just do it, and now this becomes real probability. And if you can play this game, kind of just drop this coefficient down, you're going to get something like this. And this object is called sigmoid function, and it's a very interesting function. It's essentially a little bit hand-waving thing to bring you in, but the sigmoid function is a very interesting function which have a certain properties. First of all, kind of the probability to have a class 1, in that case, we associate with a sigmoid, and the probability of the class 0, of course, will be 1 minus sigmoid. How the sigmoid is looking like? Sigmoid is looking like this. So it maps every positive entry to the number above 0.5, yeah? So, and as you increase the positive entry, you are getting more and more saturated to 1. And for the negative entries, is assign you a number which is between 0 and 0.5, but it's also have a saturation. So, and of course, kind of like when the saturation is happening is depending on the, angle, how the sigmoid is looking like. And that is strongly defined by this vector beta. Yeah. So if your beta have a large numbers, you might be very sharp. If your beta have a small numbers, you have very shallow, and you have a very kind of slow decision boundary. And essentially the classification task in that case becomes, if my probability of class 1 is greater than half, I say that it's a class 1. If my probability is for the class 0 is greater than 1, it's a class 0. But what is the training process? The training process, sorry, is just to decide what is the inclination of the sigmoid in this hyperplane, and choosing the parameters which the best describe to your system. Mathematically, formally speaking, yes, it's stated like this. And as a regression problem, if we're not kind of want to do if it's above the 1/2, it's a class 1, and if it's below 1/2, it's a class 0. This model, which is just driven by the sigmoid, just beta xi is the output of the model, is called logistic regression, which is like a first nonlinear model which you've seen so far, and which is already more powerful than the linear model. So it could predict you any number between 0 and 1, and if you can always reshape the output if you have your larger input. So you can always play this game. But if you want to use it for classification, what we're saying is that, if your sigmoid with a trained betas is giving you answer, kind of, if giving you number above 1/2, it will be class 1. Otherwise, it will be class 0. Okay, so and this becomes, this logistic regression, essentially it recovers something like linear classifiers. Okay, so but this is the very, very basic idea, and that's how you can play this game of the classifiers. Okay, so if you have a multi-class classification, so essentially you need to draw several lines. So there are several ways of playing these games. First of all, you can try to draw a separate lines between you can do it in pairs, or you can do it all together. But in that case, this approach with the proportionality of the probabilities becomes very useful because that's the universal way of defining the probability distributions. And this is called softmax or multi-class logistic regression. So you say that, the class 1 to k, each class is proportional to the corresponding bit to t of the corresponding class x. And so essentially what you have, that you have this factor on the sum of the all betas for each subclass and each probability, because, if you take each exponent on the sum of all exponents, it will be a proper probability because this is always a positive number between 0 and 1. And if you sum them all, they sum to 1. So you get a function which is called a softmax, which is essentially, for example, when used in, in the ImageNet classification, that will be your last layer of your neural network, which is going exactly to do this job. It's going to convert whatever your input data of the neural network to the bunch of probabilities using this recipe e to the z1 and some of the OZs, and you get a bunch of probabilities, and you choose the biggest probability, and that will be your class. Okay? And of course, it's defined to your model family, and this model family is called, again, it's also logistic regression, but now it's a multi-class logistic regression. And of course, it's naturally includes the binary classification because e to the 0 is just 1. Yes, and you get the sigmoid. Okay? So optimization, which optimization is used here, it's a gradient on negative log likelihood. And now now which classification metrics we need to use. So when we're minimizing negative log likelihood, we often evaluate the accuracy, but accuracy sometimes might be not the perfect metrics because, and we're going now to see what are the problems with just an accuracy. And an accuracy means it's just counting how many times you count correct answer. Yeah, so how many times, it's supposed to be class 1, and we say it's a class 1 plus how many times it's class 0, and the model is predicting class 0 and so on. Yeah, so for instance, kind of like in medical literature, sometimes what you wanted to know how many times, your algorithm is telling you that the patient is sick while the patient is healthy, and vice versa. How many you have this type of mistake, and from the other type of mistake, how many patient is healthy, but the algorithm is saying that it's sick. So kind of like you want to distinguish these two cases because that might be important, because you might want to minimize one of those things. Kind of like you might be okay that from time to time you are losing a patient who you might be okay that you misdiagnose patient, for example, but you don't want to miss the sick patient. And in that case, you want to kind of like to characterize your algorithm with that gradient. And that metric is called confusion metrics. And I think that's what we're coming to. So for the binary classification, but it's not only for the binary classification, what we can introduce the following four measurement things. It's a true positive, means that it's a class 1 and predicted class 1. If we're saying that the class 1 is positive, class 0 is negative. True negative is the class 0 and predicted class 0, yes? Actually negative and predicted negative. For example, if it's a class 1, it means, healthy. Class 0 means sick. So the patient is sick and it's predicted to be sick, and it's healthy and predicted to be healthy. Okay. So, but now we have a false negative. So, which are actually positive but predicted negative, and actually negative and false positive, it's actually negative and predicted positive. Yeah. So, and based on that, based on these four numbers, which as you see, it's a little bit more fine-grained information, because what the accuracy will just tell you is that what is a true positive plus true negative divided by the total number. Yes, because true positive, how many times we say that 1 is 1, and how many times we say that 0 is 0, and average of that. Yeah. And the error is just 1 minus accuracy, which is also do not distinguish in between the false positive and the false negatives. And sometimes it's important. And you can put it into the matrix, which is called confusion matrix, which is essentially yes. So actual class, yes, no, predicted class yes, no. So this is a true positive, this is true negative, this is a false negative, so predicted class no, actually class yes, and the false positive is the actual class no, but the predicted class yes. And based on that, and okay, so for example, simple example, so you can have a classification algorithm which is have 3 true positives, 37 true negatives, and the accuracy 80%, yeah? But which means that we just sum up these two numbers plus divided by the total number of these numbers, we're going to get 80%, but you can see that 80%, but the fact that we have too many true negatives, it's not reflecting the real situation. Yes, you think that 80% is a very good accuracy, but if you look at the numbers, you can say maybe not. Because if it's a true positive means that somebody is sick, but the people who are sick and predicted to be sick is much smaller than the error. Okay, so and also that's another thing which I don't mention, that which is here, that what you also need to, what accuracy is neglecting is what is so-called the imbalances in your data sets. Because ideally what you want, in the ideal world, you want the same number of positive and the negative examples, for the classification. And in that case, you're in so-called balanced data set. But in reality, it's not the case. For example, if you are doing, for example, classification for some astrophysical data, you observe some stars and so on and so forth, yeah? So, and you could have a very small number of events of identifying something, but a lot of negative events, yeah? So kind of like you have 100 of the good events and a million of the useless events. So, and you need to learn how to deal with that. And in this case, the approaches with these confusion matrices could be useful, okay? Okay, so, and with the imbalancing matrix, we can at least have more of the disentanglement between the positive and negative examples. Okay, so, and I think now we'll get into a little bit more from the medical literature. So what they are talking about, they're talking, and if you read, for example, kind of like about the medication or medical trials of medication or vaccines, they're talking about these two concepts, which are important, but they can also be used in somewhere else, which is called sensitivity and specificity. So, and what is a sensitivity? It's what fraction of actual positive are predicted positives. So, because, kind of like predicted positive include the actual positive plus false positive. Yeah. So, and which fraction? So, how sensitive are you? How sensitive is your test to capture actual positive? So, what is the fraction of the false negatives? Okay. So, or true positive rate. And specificity is what fraction of the actual negative are predicted negatives. You see, kind of like, because you have a false positive and or false negative and the true negatives, and you want to know how many of negative are really predicted negative. So this gives you a little bit more fine grain of your tests or of your medicine and so on and so forth. And these numbers allows you exactly to address, the corners of this confusion matrix. And we're going to see in one of the, at least in the notebooks which I have for you, there are examples of how to calculate for the binary classification problem, these confusion matrices, and we're going to see it. Okay, so, and kind of if we have a confusion matrix, what is the sensitivity? Is a true positive on the true positive plus false negatives, and the specificity is a true negative divided by the true negative plus false positives. Okay, so now we can calculate these numbers on that imbalanced example which we have, and we have a sensitivity and specificity. Okay, so there are some other ways of slicing it. There is a precision and recall. Recall is what fraction of the actual positive are predicted positive. Again, it's a true positive rate, and it's the same as the sensitivity, but it's called recall in some other content. And precision is what fraction of predicted positive are actual positives. So yes, kind of, it's also positive predictive rate, and it's used in the computer science and the natural language processing. Okay, so, and that's, recall is the same as the sensitivity, and the precision is this slicing. So essentially, this kind of more multi kind of dimensional representation of the same results of your binary classification allows you to slice and dice data with the better precision. Okay, so now we can do the same calculation and we get 3/7 and 9/7. Okay, and I think that's it for the lecture which I have for you today. And in the afternoon, I'm going to have some tutorials. So are there any questions? Or maybe I can also upload the notebook into the, because I don't see any questions. Where is my notes? I need first to upload it inside of here. Am I online? Can anybody hear me or am I talking to myself?
Yeah, we can still hear you.
Good. Okay, so let me in that case do the drop the file. Okay, so and in that case, yes. Apps. Okay. Okay. And now where is week 2? Week 2 plus file. Okay, so I dropped an IPython notebook into the in into the canvas. So let's go into that one because it will be a very simple and naive notebook. I need not only that, I also need the data set for that. Sorry, because oops, where we are? Where is my canvas? No. Okay, let me just do it quickly. Upload. Yes. Okay. Okay. So this is kind of vanilla data set of the US housing prices. And we're not now just going to apply linear regression into it. And I'm going to show you a very naive version. And I will tell you what you need to make better with that. Where are you? Okay. Okay, so it's also in the it's in the system. Okay, so now I need to stop sharing. Okay, I stopped sharing the slides. Now I need to start IPython notebook. Where is my, yes, and share my screen. Okay. Okay, so you can use Jupyter, you can use Jupyter Lab, you can use whatever you like, but or Spider. I've seen, there was some sentiments against Colab because the Colab was using AI assist, but in principle, yes, you can run it wherever you like. And this is a very, very naive and stupid way of doing linear regression, but your task will be to make it better, but one need to start somewhere. Yeah. So, and it's, taken from the GitHub and adopted from some GitHub part. So we need to import the standard uh, packages, which we will need. We'll need the pandas, we will need the matplotlib and seaborn for plotting, and we'll need the scikit-learn just now, which will load as well. So I drop this file into the canvas. Yeah. So yes, oh no, where it is. Sorry, you should be able to see it. Yes, this is the two files. Yeah. So what is the US housing data set? It's like a standard data set which have several features, which is the average income area, average house age, average area or average area number of rooms per house, and so on and so forth. There is a price, and the price we want to predict, and there is an address. Okay. So, and as I understand, you also have a little introduction to pandas, and also with the previous ones, you've seen it already. So essentially, machine learning task is we need to build a model which can predict, price. Okay, so we can check the data frame info. Yes, we just do the standard read of CSV file. And what we see that we have a 5,000 entries, which is which quite nice. And you have features. Yeah. And I think we're not going to use the address because in principle, one can use it for more fine-grained prediction, but it's making it much more difficult. We're just going to use the kind of the area income, house age, number of rooms, and so on, population and the number of bedrooms for prediction. And we're going to see how relevant it is or not. What we can do immediately, we can check the quintiles or percentages, of our features. We can also check, what are our columns. Yes, so kind of we have 5,000 entries. We can check, what is the average income according to that data set, what is the average area, house, and age, and so on. So we can also check what is the standard deviation, what is the 10%, 25%, 50, 75, and 90, and so on, and what is the maximum values. The better idea is to plot what is the correlations in the data or how the data is looking like. And for that, you can use the various approaches, but there is a built-in tool in this plotting package, which is called Seaborn, which is essentially a package which is like a matplotlib, but for pandas. It's much more data science oriented, and that's why you want to use it. And we want to plot a pair plot, which is essentially give you a correlation between the kind of you can see the distribution of the pairs and the features, and that's why the features with itself, if it's what is called the real value, it's more or less looking like a Gaussian distributed. And when it's a number of bedrooms, which is a categorical value, yes, it's like you can see how many rooms are here and there. But afterwards, also you could see, what is how the pairs of average income and average area house age are related to each other, and you see kind of you get circles, so you don't get really any relationship. But if you go to for example, the average area income and the last will be, yes, the price, yes, out of the yes. So you see that there is a relationship for the price, the fact that you don't get like a circle, but you get a little bit more kind of oval oval thing that you can see that there is a little bit of relationship between the corresponding variables, but we're going to see it in a little bit better way just now, so that we can plot it and we can see that how the data is looking like. So we can also do, we can do it with many other things, but for example, we can take a column from our data set, for example, price, and see what is how the price distributed as the histogram. So we specify number of beans and we can plot it. Of course, we can change the number of beans, and I encourage you to try it and to do it better so that you can see that it's more or less Gaussian distributed, which is good. So you can also plot it as a density again, but and there are several other things which you can just do just to look at the data, because it's very useful just to see the data and see how the data is looking like. Uh, okay. So what we can do, we can calculate the correlations between the features, and this is done using, the heat map, but for that we need to calculate the features or correlations between the numeric features. So that's what we are doing here, and we can plot it. So this function will calculate to us correlations, and of course the correlation between the same feature is 1, but you can calculate it between the different features. And what does it tell us? It tells us, roughly speaking, relationship between the features, yeah? So it's mean that, the feature number 1, the area income and the area house age are essentially unrelated to each other, a little bit of negative, but more or less unrelated. Yeah, so kind of this is a little bit stronger anti-correlation, but it's quite weakly correlated things, while the price and the area income are strongly correlated. So this is kind of a rough feeling which you can get from these kind of things. When you have a small numbers, it means that okay, and why it's also important, that we see that this feature and this feature are not related to each other. It means that you need both features, because they are both correlated with the price, but they're not related to each other. Because if two features are strongly correlated to each other, it means that you don't need both of them into your machine learning algorithm. If these two features were like 98% correlated, if the correlation was 98, it means that you can drop one of those features. It wouldn't change anything, because essentially they're describing to you the same thing. But the fact that they are quite independent, but they're correlated with the answer of your problem, with the price. It means that you need to take into account all of those features, because they are related to the price strongly. Okay, and so let me very quickly run through it, because we are almost out of time, and I will tell you what you can think about during the lunch break, and afterwards we can try to do it. Okay, so we can form the column with all the features. We need to use for the X, for the prediction, for our model training, we use these numbers. This is our predicted value, price, and the address we just ignore, because as I told you, address is interesting on the higher level. You can do the kind of the geo distribution things, but this is far beyond what we wanted to do here. Yeah, so this will be what will come into the X, and the Y will be the column that will be the only this one as a feature. Yeah, so we have our X and Y, and we can check that it have the same size. Yeah, so that we have a 5,000 entry and the five columns. Yes, and the 5,000 entries of the numbers. That's exactly what we want. We could give a look into the X's. Yes, and that we get exactly that. We by mistake don't include price. We have all our features, numeric features, and the prices are here. Yeah. So now what I mentioned to you in the lecture. Now we need to play the game of doing the splits for the test and training. So for that, again, we don't need to do it by hand. Within the scikit-learn package, there is a separate function built in, which is called train test split, which you can use. And we just standardly use it. And we're saying that we're using 30% of the data for the test and the 70% of the data for the training. Okay, so we can check the shapes of the corresponding data sets. Yes, X train and test, Y train, Y test. And what we need to see that we have the same number of entries, 3,500 in X's and Y's in the test and the training, yeah? So, and fitting the model is as simple as it gets. So again, from the same scikit linear model, we just need to take a linear regression. We create a linear regression, and now we're telling fit. Linear regression fit training data to the corresponding Y's. And these have done it. Job is done. So that's all. So essentially, we done the training, the first machine learning model. And now we can try to learn something about it. For example, we can check what is the intercept term, what are the coefficients, and what are the coefficients, in our linear models, what are betas essentially. Yes, I mean, the intercept term is the beta which corresponds to the entry one, and that's what corresponds to the features. And based on these coefficients, we would like to make a statement about the importance, but we cannot do that statement, and you can tell me why. But now also we can see, how good or how bad it is predicting what it is predicting, so we can plot out of these features how it's related to price. Yeah, and we can calculate, for example, R2 coefficient, out of the metrics, we can calculate. So prediction is also simple. Trained model which we fitted, we predicted the training data, and now we can do the prediction of the test data. Yes, and you remember the R2 is as close to 1, the closer to 1, the better. Yeah, so 919 is good enough. Yeah, so now we need to predict the test data. And afterwards, we can, for example, plot the test data, actual answers against the predicted, and we see that we're doing quite well. Yeah, so we have a little bit of spread, but we're doing quite well. And it's clear that the numbers should be good, and we can calculate all sorts of metrics. Yes, we can calculate mean squared error, we can calculate mean absolute error, and we can calculate, root mean squared, or we can also calculate, but these numbers are not telling us much, but R2 is a little bit smaller than on the training data, but it's still good enough. Yes, it's 915. Okay. So, but now the interesting job happens, because this anybody can do, and you can do very fast. Now you need to start thinking. First, let's look on these graphs. What these graphs are telling us. Lunch is coming, just a second. Because I want to give you task, and afterwards you can go for lunch. These graphs are telling us that, price is related to the income, to the age, to the number of rooms. It's not that, but it's still related. But number of bedrooms, it doesn't seem to be too much affected by the price. So, and the question is like, if we drop this variable, what will be the prediction? Is it going to change? So that's a question number one. And question number two, I spent so much time telling you the stories about normalization of the features, because let's look at our numbers. Where is our numbers? Income is a huge number. Yeah, average house age is a smaller number, because it's not a 70,000 the house age. That's a little bit too much for the house. Yeah, number of rooms and the number of and house age are comparable, or number of bedrooms, but the income is a much larger number, or area population is a much larger number. So we're dealing with the very large numbers, and ideally what we wanted to do, we want to standardize those values. So what I suggest that we do after lunch. So we're trying to, first of all, test our hypothesis that this is a useless feature, or that feature doesn't change too much, but also playing the games which I mentioned to you, at least the game of standardization. And using some other data set, we're going to play some other games with the regularization, or you can try to play the games with the regularization here. Okay? I think there are much more lunch statement than the questions in the chat, so that I think we should finish
Yes,
for now.
yeah, I think we can take lunch now. Yes, I just want to say that after lunch we have a guest speaker, and then we will continue after the first tip break.
Stop. I mean, am I? No, I think I'm at two. Yes, I'm continuing at two.
Yes, at
Yeah,
two.
because yes, 1:30 is the guest speaker, and he's speaking for half an hour, and afterwards me, tea break, and me again.
Yes.
Okay, good.
Okay.
But in the afternoon it will be only Python coding. So please make sure that you and in the afternoon the only thing which we need the packages which are in this notebook. We don't need anything for the neural networks yet. Neural networks we will need for tomorrow. Okay, enjoy your lunch.
Okay.
Evie, can you hear me?
Yeah, I can hear you.
Okay, cool. Great stuff. Do you want to check if you can share screen or
Yeah, just give me a second. I'm just climatizing to Zoom quickly.
for sure? No worries, no worries. Everyone is still on lunch, so still have some time. Four minutes.
I made a deck on the guidelines, kind of generative AI guidelines. I think it would be useful for students rather than uh, mostly just cases. So yeah, I can jump into other things as well, but we can take it as it comes.
Cool.
Let me know if it's visible.
Yeah, I can see a PowerPoint.
Cool.
So the students have been this just started Introduction to Machine Learning today, and that continues tomorrow.
Oh, that's
Just to give
nice.
just to give some context.
How's the course going though?
That's going well. Students have been quite busy.
Okay, well, that's cool. So I'm just gonna grab a water quickly. We'll be back in 2 minutes. Cool. I'm back. I'm ready when you are. Just give me a shout and I can start.
Sure, just waiting. We have a Slack workspace, and in We have a channel to communicate with all the students, all 600 odd. So we're just waiting for thumbs up from them that are ready. Then we'll begin shortly. On average, we get about 100 thumbs up out of the 600. So we try to break records here. But
more than coverage in certain brown bags, eh?
oh, for sure. If everyone can hear us. All right, I think we've got enough thumbs up. Everybody can give more thumbs up, but let's begin. So thank you, everyone. This is a special guest session. We have Mr. A.V. Moodley from the CSIR. He is a principal AI specialist with over a decade of experience leading multidisciplinary teams to successfully deliver value-driven software, data, and AI solutions across industries, including research, mining, consulting, and telecommunications. Over to you, A.V.
Thanks for the introduction. Good afternoon, everyone. Today, I'm going to talk to you guys a bit about something that is a cause of concern in some areas, but just some guidance on how to approach generative AI usage. It has given us a world of difference in the past 3 to 4 years. But with great power comes great responsibility. So I just want to walk you guys through a few tips that we kind of put forward to our organization as well as some students. This is the student version. So let me just kick it off. So in terms of some of the elements that I want to cover today, I want to go through just a brief understanding of what generative AI is, where we are in the world, and kind of how that fits into the academic environment, which most of you are currently embarking on a journey to complete your studies. Some of the core principles that are important to observe in these settings, and some use cases or some real world scenarios in which there may be elements that could resonate with you, that hopefully there's some lessons that you could learn, and just a kind of a call to action in terms of ethical and responsible AI usage, just from the perspective that most of you are in either the early phase of your careers while you are studying, or you are about to embark on the journey into the working world at some stage in the near future. And these could help you prevent certain risks as well as equip you for the world that kind of somewhat undervalues learning. So just to kick it off in terms of generative AI from a university standpoint, in late 2022, as most of you are aware, ChatGPT got unleashed on the world. And since then, there's been many other models, tools that formulate large language models in some shape or form into some useful applications. And it's been widely adopted within student communities, as it, in most cases, can fast track summarization. It can help you with brainstorming ideas. And it's also very useful for debugging your software and being able to build more effective solutions in some instances by using some of these tools. It also gives you a means of communicating and getting out your creativity, formulating ideas, structuring concepts in a way that is easy to communicate to people. So there's a lot of possibilities. However, with all of these opportunities that AI brings to your life, there's also risk. So I'll start from the kind of academic risks. We're living in an age where technical outputs or work can be submitted on the basis of nobody or no human intervention. In some instances, people are rushing under a deadline. They think that AI is going to give them the answer to meet the requirements of some assignment or some some sort of task, and they take the easy route, and those aspects can lead to significant violations on your academic journey, as well as in a professional sense once you enter the market, the job market. In your academic sense, plagiarism and your academic integrity gets compromised as a result of elements such as plagiarism. You could have inaccurate information, which negatively can affect the marks that you receive for such tasks. And it just takes you down a trajectory of risk and somewhat bad behaviors that compound and become more serious when you enter the job market and you think that this is essentially a way of working. So before we go into some of the guideline elements, there's a lot of benefits, like we've been saying. These are some of the elements where it's under, when you're doing research and you're trying to write up things that meet a certain standard. If you are in the more technical fields, the STEM fields, and you're doing skills development, or you're doing technical development, and you're working with a lot of software code, there is massive advantages that you have today that didn't exist a decade ago that you should be leveraging. But the means of you doing it is actually the important part. If I touch on, say, code debugging and learning programming languages, there's a lot of talk going around that AI replaces all of this, but AI supplements how you go about doing these types of things, but it cannot replace core logic and core understanding of certain concepts. It can replace syntax, but the critical thinking elements is what you need to develop. And you cannot live in a world where you are relying on an AI agent to fully give you all your outputs, because the question then becomes, why are we not paying for a $20 subscription rather than appointing a junior resource? And that is not a world that we want to get into, because there is concerns of dilution of intellect within the world, as well as we create a weak workforce. So part of this talk is to just give you some guardrails that you can choose to use or not, but it could serve you well on your professional journey so that you operate within the margins of what is ethical and responsible, and you also don't get yourself into trouble going forward. Before I move on, it is also very useful in formulating what you would put into your profile websites, your resumes, any sort of elements that would get you a ticket to an interview. It can also be very useful when you're doing interview preparation, going back and forth in this specific domain. What are key questions that usually get asked, and practicing how you would respond, getting feedback of what elements you can improve on. Those are viable options. And also when it comes down to improving of grammar and how you communicate, those elements can benefit you on your professional development journey. When I look at 3 core pillars of responsible generative AI usage, before you end up using any sort of tool, make sure you're picking reputable ones. If data privacy and ideas are, let's call it IP, intellectual property, is important to preserve, be careful what tools you use, because there will be hot new tools that exist every day. And some of these tools don't do the necessary due diligence in order to respect users' privacy. It may consume some of your ideas, use your data for training. Some elements are more serious than others, but there's elements that you need to consider when you're choosing what tools you use. And you have to always verify whatever outputs you receive from any sort of AI model. It is I would call it I don't want to say it's a 10x, but it is I would say it's a 50% efficiency improvement on certain rudimentary processes that you would be working on. But if you don't validate the outputs, that is under scrutiny at a later stage, or it could possibly fall through the cracks and somebody could accept it and there could be downstream implications. So it's always important to know what tool you're using and plan how you're actually going to use it and verify your outputs, and never go and put sensitive information into a third party or an open sort of AI API or system, because you don't necessarily know what privacy protection exists. And also, it's always good practice to avoid any sort of private, proprietary, and confidential information in API accessible third-party tools, just from a privacy perspective. When you're using AI tools to enhance your work or help you get an edge, make sure that you have academic integrity protocols and honor codes in place, whether it's stuff that your university decides or it's best practices that exist within the wider ecosystem of information. If it sounds a little bit dodgy, try to avoid it or rationalize why you're doing certain things. Verify your facts. Make sure that what you are producing using an AI model does not have inherent biases that could be offensive. Make sure that it's relevant, because AI models can be highly verbose and it can also depict information that looks like it's true, but it is actually incredibly false. So due diligence, making sure that you look through the information, you verify it, never copy stuff verbatim. Make sure that you are making the decision of what information or content goes into whatever you're working on and creating. And when you're done using whatever AI tools you use for gaining the efficiencies that you have, disclose it. It gives the party that is reviewing your work, whether it's a lecturer, whether it's a peer, whoever it may be, it gives them sight of what elements did AI contribute to this and what elements are actually work of your own. This just helps understand what level of scrutiny you apply to different sections. And honesty is always the best policy in this regard, because it helps you protect your integrity as well as the integrity of organizations you might end up in, or even your university for that matter. I've gone over some of these elements. The key theme that exists here is be aware of what data you are using for what purposes. When you're testing out concepts and playing around with AI tools, use open source data, generate synthetic data. Don't put your data at risk, because data is the new oil, the new gold, and data is highly valuable and important. So always be wary of what data you go and put into AI systems. If you're working on a research project and your professor sourced data from some company under some tight confidentiality agreements and you put it in an AI tool, you put your professor's career at risk. If you're working for a private company that has IP that they want to protect, say, for example, you work at a bank and there's a highly competitive environment between other banks, you don't necessarily want to cause a breach or expose your company's data to the world, because there could be implications and some could mean losing your job. So it's very important that you're grounded in principles where it's not that you're anxious about using AI tools. You know what is the line between something that is a gray area and what is right. So when you're using these tools, it's easy. It's very easy to take whatever data you have, throw it to something and ask it to do something for you. But going that extra step where you create synthetic data, or if you don't have time, use open source data. Just ensure that data protection and how you use AI tools is at the top of your mind, because that will guide you to behave in a bit more of an ethical and responsible way. And I know a lot of this conversation sounds like I'm giving you guys a lecture on how to use these tools, and not focusing on the positive side of it. Rather, I'm giving you warnings about some of the bad things that could happen. I'm doing that because there's a lot of evidence out there on cool applications, and in another session I can go in deep on that. But I feel like this is critically important for us to be able to set you up for moving forward into your career with a grounding into how you use AI responsibly, because that is going to be critical in the new age that you're walking into. Doing stuff that gets you into trouble kind of nullifies that. So that's why the focus is here. And sorry, 1 second. Yeah, so if I look at some real world situations that maybe some can align to, the first scenario, John uses ChatGPT to write his history essay and submitted it without looking through anything. The AI included fabricated references, and his professor immediately picks it up. He receives a 0. Might be a bit drastic, but in plagiarism cases, that does happen, and got reported for academic dishonesty. It is very important to fact check. A personal example for myself, when ChatGPT and models of this nature started emerging, and I would have conversations with it to kind of conceptualize certain research concepts. The first time it gave me references, I was so impressed. I thought, wow, there's actually work that's perfectly aligned for what I'm talking about. And I couldn't wait to go and get access to those papers just to have a look at what did these people actually do, only to find that those papers don't exist. And that it created a bit of distrust in me in terms of the information that I receive. And there's been many instances of professionals making these errors. Recently, Deloitte got into trouble because facts that they represented in certain reports were inaccurate and actually AI hallucinations. And there were severe repercussions for the company because of the actions of professionals in that environment. And the same goes in an academic sense. On the next one, it speaks about you're doing research and collecting information of some topic that you're looking at, but in the same breath, you're collecting people's personal information, and you're lazy to clean the data up. You just want to take that Excel that the survey spat out, and you want to put it into AI to give you a view of how all of this fits in. But in that way, you do expose some personal information, and that could be a significant risk, especially when you work in an organization that has strong policies around privacy. And in South Africa, POPIA kind of governs a lot of that. So it's not just organizations like big corporates, it'll be universities, it'll be government entities, it'll be research organizations like the CSIR, and there can be serious implications for privacy violations. So even if your work is brilliant, these are some of the caveats that could get you in trouble when you didn't intend to get in trouble, or when you didn't aim for your actions to end up with severe consequences. So it's more just views on how you can protect yourself from lessons we've seen happen in the real world, and elements that are academically agreed on across people working within the AI space. And yeah, these go back into some of the bigger details on copying code, basically speaks to the elements of copying things verbatim and the challenges that could incur from that. So yeah, on the citation thing, just be sure to verify all your citations. You can avoid a lot of trouble by just investing that little bit of extra work. And when it comes down to code development, part of it is for you to learn. You're in a phase of your career where you need to learn and absorb all the information that you can. And when you use AI tools as the primary force of executing to get an output, you don't activate your brain to actually absorb the information of the how, the why, and the inner details of what went into the system. And in many cases, you are expected to defend orally what you have created. So in those situations, you don't want to be embarrassed or exposed for not knowing what is in the code that you submitted because an AI generated it. If there's a critical bug, you could be the bottleneck between the solution being fixed or people being sitting with it for days because nobody knows where that variable that was vibe coded actually exists. So make sure you understand what's in your code. Make sure that you understand when you're writing papers or documenting the work that you're doing. The information should be a true reflection of the work that was done. And sometimes when you use AI haphazardly, that can go significantly wrong. So yeah, then these are just a few myths that exist. Firstly, the big one for me, AI makes learning unnecessary. If we operate with that mentality where you don't need to learn because AI will do it for me, you decrease the value that you add to the world. And you basically take yourself out of a race where if there's many people competing to be successful in a space, those that are able to think for themselves gain that advantage over those that are hyper reliant on AI tools. You need to have a balance when you're using AI tools, just so that you understand the value that you bring is yourself, not your ability to type into a keyboard to an AI model. The next one, AI outputs are neutral. AI models are biased by the data that they are trained on. When I say AI models, I mean LLMs in this sense. And a lot of that bias comes from the data sets being trained on being highly westernized because of a lack of digital data in Africa. And elements get misrepresented, stereotypes get perpetuated, and when you're writing using an AI model and you're not observant of these things, you could inherently pass on those biases via your outputs, and it could be represented as your view, whether it is your view or not. I spoke about the free AI tools to some extent earlier, but if you are getting access to any free tooling, you are the product because they are harvesting your data. And it's fine in most contexts, but you need to just be aware of it and understand what is getting taken away from you. For those that are going to venture into startups and entrepreneurship, you need to be very safe with your IP because you don't know how it's getting exposed. Obviously, the big Googles and Microsofts are not, no, in most cases, the big Google and Microsoft companies are not going to come in try and take your IP, but you never know. Any exposure could expose your ideas. Another one is professors can't detect AI usage. I've reviewed quite a few applications over the past few years for events and workshops. And what I've found is it becomes very easy to pick up the style patterns of AI. And you automatically invalidate your work if it is AI heavy, where it looks like there isn't any human intervention here. Also, if your friends are using AI irresponsibly, it doesn't mean that you should use AI irresponsibly. You need to think about the world that you live in and the integrity that matters to you. If that is a key factor for you, please do behave responsibly and ethically. If it's not, maybe the presentation wasn't for you as an audience, but I strongly advocate that everyone should try as hard as they can to make sure that you are using AI in the most responsible and ethical manner as possible. And yeah, just to conclude, I hope that large parts of the audience today will commit to using AI responsibly. Use it and make it your superpower. Make it into, I like using the analogy of Iron Man, make it into your suit that makes you into a superhuman, but be the brain that controls that. Don't let it control who you become. So yeah, with that said, I'd like to say thank you. And I hope that you would use AI's potential for the good and take the necessary measures so that you use it responsibly and effectively. Thank you.
Cool. Thank you so much, Evie. That was really insightful. There's actually a question which I think is quite relevant and in line with what you're actually doing. So the question on the chat here is, I'm excited to see if different LMs start popping up with different training data rather than Gemini or ChatGPT train on Western data. We need Africa GPT and Ubuntu GPT. Maybe you can speak to that a lot closer because they actually are developing that at CSR.
Yeah, 100%. Thank you for that question. So data is a challenge, but we're on that journey in partnership with CHPC and some other colleagues in CSIR to enable that to be a possibility. So it is a journey to just build large language models. So right now we focus more on how can we build small language models that are comparable in performance, but cater to the environment that exists in Africa, where we don't necessarily have big compute power at our disposal in multiple locations. We need to be strategic with our resources. So we're trying to advocate for effectively use models rather than the big bad models that you would see coming out of the likes of OpenAI and Anthropic. So some of the challenges that come with that is capturing and digitizing data. For most of the South African languages, they are heavily under-resourced, but we are on that journey to collect enough data and modify techniques for the local South African and African context so that we are able to build custom models with our own architectures that can service the needs of the country, because it is highly frustrating to use some other models. As an example, I asked for a generation of South African money the other day. Nelson Mandela looked completely different. The animal on the 10 rand was a hybrid of a rhino, a lion, and an elephant. It does weird things, but if you had basic context of our context, it would succeed as these things. So yeah, it's a very relevant problem that we're trying to tackle. And if there are students that are interested in these sorts of areas, please do reach out. We're always looking for people that are excited to join the mission. And yeah, could be something cool that you get to experiment with.
Cool, thanks, Evie. We have ran out of time. There are more questions, but I will forward it to you, and you can maybe respond it via email. I think it was quite insightful. We are taking up time for Prof. Ilya to continue machine learning. So just want to say thank you again so much for this presentation.
Thanks everyone. Cheers. Bye.
Hi, everyone. I hope you had a nice lecture. And yeah, so let's continue with our exercises. And did anyone try to do something extra, or everybody was too busy with lunch? Okay. I know that you just came up with the presentation, but before that, nobody. Okay, good. In that case, let's go into the code which I shared just before lunch, and let's try to play with that. Let me share my screen. And can I also add a couple of cents on the questions of the previous talk, like, any tips on AI generated work? At least, with the text, it's relatively straightforward. After you read a few, it doesn't have depth. It's usually a very simple thing. Like, it could be a text which is, if you read a text which is written on a very elaborate, wonderful English, and this text, but it doesn't have meaning, it's very likely AI generated text. So that is why some of you who are writing motivation letters don't use ChatGPT to generate for you a motivation letter, because it will be very averaged, kind of empty letter, which is written with a high English, which you might be not using in any of your life activities, and it will be clear that you haven't put an effort into the doing real motivation. Of course, it's much more difficult with images, but there are other approaches as well. So with images, you need to count fingers of the humans. Okay. So I hope that everybody have the file and everybody can run it step by step. Oops, where is my Slack? And also about the AI guidance. Most of you are students, and many universities, like for example, University of KwaZulu-Natal, have its own kind of like UKZN Gen AI policy, so that you can find these documents in the policy documents of your universities, and most of universities are now having them. So you can find out what your particular university is finding acceptable and not acceptable, because there might be things which you think are acceptable, or common sense is telling you that they're acceptable, but your university might find it completely unacceptable, so that you should try to avoid that. Okay, so let's go through the notebook again, because I already run the notebook. So I assume that you've seen most of the packages which I use. Yes, NumPy, Pandas, and Matplotlib you were supposed to see in the previous days. Is it correct statement? Yeah, and have you seen the Seaborn or not? Okay, very good. So essentially, there is nothing new on this side, so that you can upload the data set. Yeah, we can check that the data set is good, and it have all the entries. We could see what the entries is, and I kind of before the lunch I told you about that we can see the pairwise plot, and for that we need a Seaborn, because it just make it easy. Yeah, so we could also see some other statistics, and it's also very useful to see that the distribution of the values. Yeah. So, and afterwards we could calculate, the correlation metrics between the different values. And as I mentioned to you, the correlation metrics can give us the idea what is important and what is not important in our data set, and is that all the features are important or not. And we could have all the features. We could do the separation. Did everybody understand what this part of the code is doing? So that we have, a list of columns, and after we have a list, we can slice the list. Because I assume that probably last week you had a little introduction into the NumPy and the list and how to slice them. Zoom in. Okay, sorry. Okay, yeah. No, just oops. Can I? Okay. Is that better? What's the purpose of the line matplotlib inline? Okay, so that's an interesting question. So what could be the who knows the answer? You mean this one, yeah? Did anybody know the answer? Yeah, good. Yes, exactly. It's make them okay, matplotlib images, but also the seaborn images render inline within the code. Yes. So if you transfer it to the Python and you run it into the Spider, you need to comment it out. Okay. So this is just a little thing so that we can see the images inside of the notebook. But also, I highly encourage to do the following. Yeah. I assume that you can see my screen and you can see, yes, what do I see now? Yeah. Is a special IPython magic command used environment da 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 da. Okay. So, and as I mentioned, yes, if you are doing it in the Spider, you need to comment it out. You don't need these things. Okay, so this we can do. This, I don't know. I just not sure how much do you want me to comment on the code, because I already quickly ran through the code. Okay, I get again request to zoom in, but I'm not sure how far more I can zoom in, because I'm already the 100% width. If I would do more zoom in, I will be just you wouldn't see the full width of the notebook. But just run it in your Jupyter lab or Jupyter. Okay, somebody is saying that it's better now. Okay. Okay, have anybody managed to run the notebook and get the similar results? Or do you want me to run through the notebook again? Okay, somebody did. Good. More? Okay, yes. You can also do it on VS Code, and on VS Code you can have a IPython plugin that you'll see the IPython notebook. Yeah. Okay, good. So, but this is a very simplistic and very primitive notebook, which does not respect anything what I told you in the lectures, yeah? So now we need to make it a little bit more fancier or a little bit better. So the first thing which we've seen with you from our predictions, so that just looking on these images where we're looking at how the different features are related to the price, that's, the number of bedrooms and the price are not that related to each other. Yeah. So, and the question is, can we check this hypothesis? Can you guys now take away out of your X data set, out of test and training, take away this feature and rerun the linear regression, and we can compare our two scores? Can you do that? No, we don't have here we don't yet have a validation split. If you want to do the validation, you need to do a slightly different comment. You first do test and training split, and after you take your training data and you push it into the k-fold cross-validation procedure or stratified k-fold cross-validation procedure, which is going to cut out of your training your validation set automatically. And we'll do the shuffling because, if we want the validation to be not fixed in one spot, we want it to be kind of like distributed with respect to the folds. It's better to use a special comment for that. But I think that will have in the next notebook. This is very, very basic because we don't have here, because why do we need validation if we need to do the optimization of hyperparameters? But we don't have here any hyperparameters. So in principle, we don't need the validation. The only thing what we can do, we can just try to make sure that, when we do the test and training split, that it's representative enough. And for that, we need to know which parameter of the test and training split is doing that. And because, now when we're doing test and training split, you say that, okay, we use the X for the X's, Y's for the labels, 30% to the test and 70 to the training split. And of course, we'll fix the random seed, but it doesn't tell you anything about, do we get the data which represented from the same distribution? I mean, roughly speaking, what could happen just by chance? Let me go in one of the pictures, for example, into this one. Yes, just by chance, you could get to the training data this half of the Gaussian and to the test data that part of the Gaussian, which is not a good thing. Yeah, because kind of your test and training data are represented on the different parts of your distribution, and ideally you wanted to see that they're represented on the same part of your distribution into the features and in the labels, because in that case you could hope that your machine learning algorithm will work well. And of course, because this is a standard feature, it's supposed to be already implemented. So in order to find how it's implemented, what do we need to do? We just need to go again here and yeah, and already there is a correct word. Yeah, so we go to the documentation and we're looking at the parameters. Yeah, so this is our input arrays. It's a test size, which we can specify or not specify, train size, yes, random state. And we have here a couple of more parameters. Shuffle. Shuffle means that, sometimes what you have, when you build your data set, you might, if it's synthetic data set or if it's something like that, so you could have, all the, for example, ones, first if it's classification task and afterwards all the entries for the zeros. Yeah. And in that case, what you want that, the system also do the automatic shuffling. In that case, you do the shuffle true. And if you don't do the shuffle true, it might be that your data is already, if it's already prepared data set, many packages are coming with a pre-prepared data sets, so they already shuffled good enough. And the thing which is going to guarantee to us the same representation is exactly this parameter, stratify. And we can just go down and read. Okay, So if we want to make sure that they are represented from the same distribution, we need to stratify it and change it. Default is none, but we need to change it to yes. Okay. Okay, good. Okay, do you want to try to do the same game, but without this feature? Yeah, you're getting, yeah, we have the first answer. Yes, we are getting roughly the same answer. And I think that's what's really telling you that, okay, it doesn't matter from the point of view, kind of it's really irrelevant feature because does not affect, at least, to the level of the precision which we do the R2 score. And so it doesn't have much explanatory power. And if we go into the notebook, if we go to the bottom, we will see that, I even already have a little code here, which is just dropping out the corresponding bit. So now, when we drop it from the axis, what we need to do, obviously, now we need to do again the test training split and just copy and paste the code. So let's do it quickly. So we can check that it looks the same way. So that the shapes are correct. No, the shapes are not correct. Yeah, because it's not supposed to be 5, it's supposed to be 4. What? Because I haven't run it. Yeah, sorry. Okay, good. Okay. And now we just keep copy and pasting because all of that is already run. So we can call the model slightly different. Linear model shot. And we can train it. So if we want to compare with the same. Okay, but we also should have probably changed the name of the training test, but okay. Okay, it's very quickly to get trained. Okay. Now we can play this game because this is, yes, so 0, 1. Is it R squared on the training data or on the test data, which is in the chat 0, 1, 9? Because this was on the training data in the previous one. $10. And yeah, just check R squared. We can check everything else, but R squared will be good enough. His predictions. Yeah, okay, yes. So we're getting the same results essentially, yeah? So neither R squared on the training data, neither R squared on the test data is affected. Essentially, that feature wasn't really, and these guys are affected. What is MSE? Yeah, I mean, but you see that's a problem of dealing with non-standard features. We're getting huge numbers. Yeah, they're slightly affected. but one cannot make any conclusive statements because our features are not normalized. Okay, so that would be the next step. Are you following me? Or other people lost? Okay, good. So now so at least it's one following. And I know that there's two following people because one row, one run the code and wrote the numbers, and one more is just following. Okay, good. Okay, so there's lost person. So, and where are you lost? What's exactly you want me to go over again? Okay, so where the code was copied. Okay. Let me just go back to that code. But essentially, it's absolutely the same code as we have before, because what you need to understand kind of what we're trying to do. We're trying to, because I have this code which we run, and you also have it in Canvas, and our original model have 5 features. Yeah. So and now what we want to see by just purely just kind of like eyeballing the graphs, we could see that, this feature is important for the price. So there is a relationship between the price and this feature. There is a relationship between this feature and the price. The same applied here and here. And clearly here is the strongest one. And you see that these ones are weaker because it's more circular. It's more kind of a little bit of random thing. But if you look on this one, what we could see is so that, average number of bedrooms is not really affecting the price, kind of like, it's not like it's going up, 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 up. So the more bedrooms, the higher the price is overall. It's kind of the number of bedrooms is not the primary variable, clearly. And what we want to do, we just, okay, let's remove this thing. So how can we remove this thing? We can get our columns as in previous one. And now we need to drop one column. And which column we need to drop? That one which corresponds to that feature. So we can just count which column it's going to be. Yeah. So because this is column number 0, 1, 2, 3. And we're dropping this column. And now we can just, and also we're dropping the kind of the y's is the same y's. But now we're just checking that we have dropped the right column. So, and what we have area income, house age, number of rooms, and population. And we don't have any more number of bedrooms. It means that we have dropped correct column. And we could not have done it like this. We can also have done it, I'm sure that you have it in the pandas examples that you can, if we just use the name of the column. So if this sounds a little bit confusing, this counting argument, you can just use the yes, in the Canvas there is a copy of this notebook, but I think that the copy in which the student is asking is about the copying of the text. So okay, so now we have an X which have one less column, and now we just need to play the same game because X now is contain everything. I just copy from my previous code test and training split, and I run it identically the same. Yeah, so this is this line, train test split, because we need to split this X and Y's, X features, input features, and the labels into the training and test. And we use absolutely the same code. But now what we wanted to check that we it's split it correctly. So we can check just the dimensions just to see that, okay, so in the training we have 30%, so 3,500 and the 4 columns. In the test, we have 1,500 and the 4 columns. And in the Y's, in the labels, we have 3,500 of the numbers and the 1,500 numbers. And now we're just doing the same thing because we already loaded the linear regression as a model. So we're creating a new model. We're doing the standard fit, but now X train and Y train are these ones. We get a trained model immediately because it's very easy to fit, and there is some list of parameters and blah, blah, blah. And now we could immediately check what would be prediction on the training data set. So we do trained model dot predict, and this is a universal thing, for example, for scikit-learn. It have a whole bunch of models, but it's also be dot fit. Oh, you load the model and afterwards dot fit dot predict. So irrelevant what it is. Would it be logistic regression? Would it be, support vector machines or random forest or decision tree or whatever? So dot predict X train. So we have get a list here of the train labels. And now we need to compare it to the ground truth. So Y train and train prediction, and we just calculate R2, and it's exactly the same R2 as we have before. So kind of the dropping out of the feature doesn't affect the performance, while in theory, if this feature was important, the R2 score was supposed to go down. But R2 score remained the same, at least up to the precision which we have in the R2 score. So it means that it's really zero effect. Yeah. So, but the performance on the training set is the one thing, but we also want to see what is the performance on the test set. So when we do again, our new trained model predict X test, and we again check the R2 score. And it's again absolutely the same. So the only thing where we see in which metrics do we see some little change is in this mean squared error, Maya, or root mean squared error. There is a little change in these numbers compared to that numbers. But what I mentioned to you, one should take it a little bit careful, these numbers, because we haven't done any normalization of the data set or standardization. And the problem with our data set is if we look where it is, yeah, kind of here, that our entries have a very different scale. And this is always bad. So because average income is a number with 4 or 5 digits or 6 digits. Average house age is the number usually from 0 to 10 or 0 to 10 number of rooms. Average number of bedrooms is also from 0 to 10, yeah. And the area population is again number with 5, 6, 7 digits. Or essentially we have the statistics. We can see what is the maximum. Where we have we have here the maximum. Here is the maximum, a number with 6 digits. This is the 1 digit essentially. This is okay, maximum 2 digits, but 10 of the order of 1 digit, and again we get 5 digits. Yeah. So now we're shoving all these numbers, which lives on the completely different scales, into one vector and giving to algorithm to train. And it's not really surprising that the algorithm is a little bit, given to us coefficients like betas from the lecture, which are a little bit kind of hard to interpret or hard to judge importance. Okay, so now the question is how we can play this game. And in order to play this game correctly, okay, somebody helped, yes, with the pip install scikit-learn. Very good, thank you. Yeah, so in order to play this game correctly, what do we need to do? We need to take our input features and standardize them. So, and this is our next attempt within this problem, and afterwards we'll go to the more fancy notebook. So, how to do the standardization? Again, we need to go, again, the scikit-learn is such a nice library so that it's contain most of the functions which we need for some kind of like non-neural network type machine learning. For the neural network type machine learning, I mean, it has some basic capabilities, but it's better to go for more specialized packages like TensorFlow or PyTorch. Let's Mean okay, that's what we want, but I want to see. Okay, it's a unit which is called preprocessing, yeah. And then in scikit-learn there is a preprocessing, and you have several options how you can do the preprocess for the different things. But what we're interested in different scalings, because there is this min-max scale. Essentially, it's just take your minimum and maximum value and scale all the values in your data set between those two numbers. But that's not usually, sometimes it's not a good idea. Or what we're doing, we're, normalize is doing slightly different. No, is exactly what standard scaling, yes. So exactly what we have in the lecture. In the lecture notes, we were doing this. Yeah. So now we need to apply this function, standard scaling, to our data. How we're going to do it? Any suggestions? Okay, so no suggestions in the chat. Okay, so in that case, what do we do? I mean, of course, nowadays you have two options. The option number one is what I'm showing you, and kind of one of the approaches to the option number two, you was just told in the lecture before that you need to use a generative AI and you need to ask ChatGPT. Okay, so but I suggest to you old style option, and we go to the scikit-learn manual, and we see the example. Yeah, because that's exactly what I suggest that we try to do. So we replace our features by the feature minus average divided by the variance. And which is very nicely is usually what do we have? We have that it's also giving us example. Yeah, so we have a data. We need to create a standard scalar, and we need to feed the data. And afterwards, we need to transform the data. Okay? But this example is, in fact, is a bad example. And who can tell me why it's a bad example? And do we have a better example? Okay, I don't see a better example, but we'll now. Any assumptions why this example could be bad? Okay, nobody's typing. Okay, good. Why this example is bad? Because it's shown to us how to do the user standard scalar, but because in this example the data is so small, it's suggesting us to do it to the whole data. And this is a very bad idea. So if I now will start typing and going to do the standard scaling to the all data, which include the training and test data, what will happen? I'm going to inadvertently to pass some information about the test data into the training data, because the information about means and variance from the test data will be in the generic category. Are you following my argument? So, and what we need to do, we need to do the fitting of the standard scalar. So we need to measure the mean and variance based on the training data. transform the training data based on those numbers, and also transform in the same way test data, such that there is no information about the test data is passed to the training data. So if we just do a standard scaler for the whole data set, what is going to happen? We're going to do so-called contamination of our data. Are you following my argument? Okay, very good. So now, but because this is a very subtle point, because sometimes and you need to be very, very careful. Otherwise, kind of in this particular case, it wouldn't matter that much. But for example, if you use some standard scaling, kind of some other scaling approaches, you're really contaminating your data. I mean, in this case, I don't think that, but I mean, even in these cases, might make a difference. So one can try and see. But let's go for it. So we're still going to use an example, but now what we're going to do, okay, so what we're going to do, we need to do the standard scaling, but we need to do it after we have done the test training split, okay? So what we need to do for that one, we need to go back to our stage when we have still all 5 features, or we can do it with 4 features, it doesn't matter. Okay, let's do it with the 4 features so that I don't need to waste time on redoing it. So we have our test and training data here. Yes, but it's a 4 feature one. And let's do the, first of all, we need, yes, to load the standard scaler. Okay. Now the next is we need to initialize it. Oops. Okay, so and now what we need to do, we need to do this game, but this game we need to play only on training data. Yeah. So, and okay, so let's try and see. So fit, and here we write just X train, Y train. Yeah. And let's see what's happening. Okay, so we have created our standard scaler, which we're going. So essentially, what have it done? It's used the training data X and Y, yes, to calculate what is the mean and the variance in the data, in the training data only. And now we're going to apply this procedure, yes, kind of normalization of our data based on only training data. So we're going to subtract from every feature its mean and divide it by variance only on the training data, but we're going to apply it to the training data, of course, but also to the test data. And afterwards, we're going to redo the machine learning part or training of the linear model. Okay. Good. Okay, perfect. Okay, so now let's do the, how does it do the data transform? Scale transform that we, okay, so we could have that. No, I mean, fit transform is not, where is just transform? I just wanted to see what does it. Okay. Perform the synthesization and center and scaling. Take it in. And what does it return? Returns, yes, X transform and DRA sparse matrix of shape and samples and features, transformed array. Okay, so the question is, what do we do with Y's? Or Y's, we're not supposed to transform Y's as well. Okay, so let's see. So if, to be honest, I don't remember that because I want you to do that. Okay, scalar, transform. And now we do the, X trained SC. Let's go transform, yes, and we do the, okay. Okay, so and this guy is supposed to have the same shape, yeah. And now X test scaled will be scalar transform X test, yeah. Oops, okay, good. So now let's try to do the same thing. Now let's redo the training. And let's see what are we getting. Can you do it or should I type it? Okay, essentially we just copy the same thing. We need this one, yeah, for the scaled guys, but let's just put it into the one thing. We need to do the fitting of the model. Yeah. And now next. Have we fitted the model? Now we just need to do prediction. Ah, no, sorry. Typo. Ding, ding, ding. Train predict. Okay. And what have we learned? It doesn't change anything. Okay, and now let's do on the test prediction. Yes, it literally doesn't change anything. Okay, but let's look on the coefficients. And can we learn anything from coefficients? Let's copy this one. Okay. Okay. Now, but at least these numbers make a little bit more sense. Because if you compare now these numbers, our list of betas to this list of betas which we had before. Yes, kind of like when we've done the first training, when we've done just the first training, this was our list of betas. When we take from our model .coef, it's give us, beta 1, beta 2, beta 3, and so on, and also intercept term. Okay. Okay, and okay, we can also get the intercept over there, but this is just a constant. But because our input values, x's, are in a different scale, it's very difficult to say what does it mean that average area income beat the coefficient which correspond to that feature is 21, while for the house age is 165,000. So does it mean that this is more important feature or not? But now, because what have we done by scaling, although we haven't learned anything, or we haven't improved R2 score, for example, but what we can learn now, because now our excess or input data are features on the same scale, because we normalize them and divide by variance, now we can say that, that the predominant factor, because now these numbers are making sense. And what these numbers are telling us, because they are all going to be multiplied by the number which is coming from the Gaussian distribution with the zero mean and the variance of 1. So by far, or not by far, but I mean, the biggest contributor for the price of the house is average area income. And afterwards, house age, and you get, two other features, area population is the factor, and the least important feature out of those is number of rooms. Yes, because it has the smallest coefficient. Yes, but the dominant coefficient is the average area income. And why this exercise is important? Because now, if you imagine that, okay, we have a naive and simple data set, but if we would have, a data set where you want to build some, I don't know, you're analyzing some experiment which really have sense, or you need to build the model of something, and you have, a 200 or 300 input variables. After you have done this game and you have a list of coefficients, and kind of like also in nonlinear models you can have a rankings of the inputs, or ranking of the features. Now you could say that, okay, so if I want to approximate, or the most important factor is, which is supposed to be built in my theory, will be the coefficient which correspond to the biggest input to the answer. Okay, so kind of, and afterwards, this is next to important, and so on and so forth. So that you can build a kind of a plausible model, what's give you kind of the results as in your model. For example, if you build in the model of some physical system and you have some observations and so on, you can understand what are the most important factors in the model of your system. Okay, are we good? Can anybody suggest why R2 score doesn't change in this situation? Or why the scores, change only marginally? We have that in the lecture. Anyone? And standard scalar is a linear transformation which does not change your variance. And what does it change? Of course, it's a linear transformation. It's a right way of thinking, but it's not everything what I want to hear. I want some more addition. Okay, somebody's typing. Yeah, the question is why, we've done all these games of applying standard scalar, and I was telling you that we need to standardize the features and blah, 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 but the result is the same. R2 score is the same, and we've seen like, so that it looks like, we just wasted the time. In fact, we haven't wasted the time, as I mentioned that, we can have now ranking of the coefficients or betas in importance, but, also it would be nice to understand why the R2 score remains the same, although we apply standard scalar. And the suggestion of Alex that the standard scalar is a linear transformation which does not change your variance is a good point, but in the lectures it was explicitly answered, and we could also see it in this notebook. What the standard scaler have done to us. Okay, I think what happens and what I'm trying to aim you at, that because we don't have with you any regularization in the system. So when we have a standard scalar, which is your feature minus a constant divided by a number, minus a constant we can neglect because in the process of training it just outsourced. But this divided by a feature is just getting shoved into the betas. And our betas, which were before numbers on the different scale, where they are, yes. You see kind of here's a 2-digit number, here is again a 6-digit number, and so on. Now, why these numbers are so different? Because the x's were on the different scale. Now we bring them to the same scale. It means that something we need to multiply by something, something divide by something, but these prefactors just jump into the betas. Okay? So that's why it's kind of, yes, it's a little bit of reshuffling of our data, but it doesn't affect the R2 score, and so that is in principle understandable. And if we want to affect the R2 score by doing the games like that, what else do we need to do? We need to add regularization. So we need to add L1 and L2 regularization and start playing this and doing the hyperparameter search. Okay? But we're not going to do it in this notebook because I think we're going to do it in the next notebook, because now when we're going to do the hyperparameter search, it's going to be a little bit more involved. So, do you have any questions by this notebook? Otherwise, I'm going to switch to the next one. Okay, yes, I will. I will share this one. Save all. Okay, let me stop sharing. And let's go to the next one. And for that, so that you have access to it, I need to upload it. Okay, so let me do save all, close down. And now we go into these two. And yeah, okay, so let me upload it into the canvas first. Okay, and let me make it visible. Okay. So now we're going to drop. We're going to deal with fancy regression, and we're going to talk about wine. Okay. And the data set, where is my wine? Is this one? Okay, so now there is two new notebooks now should be available in the canvas. Okay, and the new data set, which is a wine quality data set. Okay, so let me Okay, let me share my screen again. Okay, so I assume that everybody could see my screen. And first, we're going to start advanced regression example wine, and afterwards, advanced regression example CLF. Okay? Again, yes, I haven't invented this notebook. I adopted it and I attach in a source. Yeah, so again, we need, the same packages. Yeah, so we're going to use NumPy, Pandas, scikit-learn, and Seaborn. Let it load. Okay, so we can pick up the CSV file. And essentially, what are we dealing with? We're dealing with the wine rating data set. And essentially, yes, we have some parameters or features, yes, acidity, this type of acidity, that type of acidity, residual sugar, chlorides, and so on and so forth. And there is also our label is a quality, so it's a kind of the rating of the corresponding wine. Yeah. And first of all, we can check what are we dealing with. Yeah, and we're dealing with 4,898 entries, and they're all of them are there because it's a standard curated data set. So there is non-null entries and everything seems to be fine. So we can play the same game with the pair plot and see, do we see some obvious. Yeah, you should apply standard scalar by default. There is a question. Okay, so I understand that regularization does not affect R value, but okay, sorry, okay. So I understand that regularization, no, I mean, regularization will affect the R value. Yes, because that weighting will play a role. But why it doesn't change MSE? Yeah, it doesn't change MSE because I mean it's not about regularization. The absence of the standard scaling doesn't change MSE or doesn't change it drastically because you're just shifting the coefficient on which you are dividing value into the beta. And that's why kind of like beta x is the same, irrelevant of as it was in the lectures. Where is the lecture? Where is the lecture note? Just give me a sec. Okay. Where is D1? Take it in. Okay. Boom. Sorry, let me just find the correct slide from the lecture. Yes, this is a slide. View full screen. Okay, and now I need to share it. Where is my Zoom? My Zoom is here. No, where are you? Here you are. Yeah, we have feature standardization thing. Yeah, so, and what this standard scaler is doing, it's subtracting a value, but also it's dividing by it. So kind of like it's scaling it. But in that case, this scale is just in the process of training of the betas, is shoved down on betas. Okay, so and that's why beta scaled beta on scaled x is the same value, and that's why it doesn't make any difference. Of course, from this point of the analysis of the model, as I mentioned to you, because now we standardize x's, the relationship between betas we can interpret. We can say which beta coefficient is more important, which beta coefficient is less important to deal with explainability of the model. In the moment when we add regularization, when we're doing these games of the rescaling, yeah, it's going to affect this term because it's not going to cancel out. So if we have done the same game, and I will show you now kind of like on the line data set, because we need to build not linear regression, but there will be linear regression with regularizations are called differently in the scikit-learn. One can play this game and see that you can do it on the standardized data set and not standardized data set and see what's happening. Okay, so but that's a rough intuition. I was supposed to have a break. To kill you?
Yes, yes.
Okay, good. Okay, so what is the break? For how long?
15 minutes.
Okay,
Yes.
15 minutes starts now.
Yeah. So we resume at 15:15.
Yeah, and people who haven't managed to download the notebooks, you can download them now.
Yeah.
Are we back?
Yes, I see thumbs up on Slack.
Okay. Good. Okay, good. Let's dive into the new notebook. Yes, and I updated the previous notebook with whatever I cooked up. Okay, let's go into here. Okay, so I assume that you all could see my screen, yeah? So, and we're going to grab the data set, and as I told you that the data set is just, bunch of features which corresponds to the different properties of the wine, and afterwards there is a rating of the wine. Okay, good. So where we were, we have done the info, and we've seen that the all features are full. That's all good. So now we can do the pair plot again and think, are we getting to learn anything or not from that? Yes, so kind of like we get this nice figures which are telling us, how each feature are related to each other, and we could see that, there is somewhere there is a relationship between things, yeah, and somewhere there is a very weak relationship between things. So essentially, okay. So we could not see clearly things, but also interestingly, like there are points which are lying outside of the bunches of the points, which are usually called outliers. So kind of like, and they are usually creating some problems for the prediction models and things like that. So there is a special part of within the machine learning which is dealing with of the finding the outliers within your statistics and things like that. Okay, so again, similar to the previous case, we can do the heat map and we can see how the features are related to each other and how do we have a strong correlation, weak correlation between the features. And we could see that, there is a weak correlation, somewhere there is a stronger, like, 0.29, so 0.3 is a stronger correlation, but there is no, like, 90 or 80% correlated features, means that they all play a role, and we can also see how those features kind of like straightforwardly related to the last feature, which is the quality, which we are going to try to learn how to predict. Yeah, so when we have that it's correlated, something is poorly correlated, for example the citric acidity seems to be like quite irrelevant, others are more, others are less. Yeah, so free sulfur dioxide is also, it's probably not the factor which determined which wine people are drinking. Okay, but I mean clearly the runner-up is the alcohol content, which is a little bit disappointing. But what can you do? Okay. Okay, so now what we need to do, we need to do the test train split, and we also need to do the scalar. Yeah. So quality is our prediction value. We need to drop it. Yeah. So data.drop name of so that's another way of how you can drop the columns. Here's the name of the column, and x1 means that you need to drop the column, not row. Yeah. Yeah. And now we're doing x train x test, y train y test. We're doing again the same train test split. Again, the test size is 30%, and some fixing some random state. And afterwards, we immediately initializing standard scalar, so bringing the features to the same normal distribution, and fit transform of training data and transform test data. Okay. And again, the stupidest thing which we can do, or simplest thing which we can do the linear regression. So we can do the linear regression, and we can see what have we learned from the linear regression. So, and we learned that, our MSE is 0.55, or on the training, on the test is 0.587, but, we don't know how much, what's the value, and we can do R2 score, which is a little bit better thing which we wanted to see, and R2 score is quite low, yeah, because R2 score, if it's good, it's supposed, you remember that in the last case we have out of the box 90. Yes, 0.919, 0.915, and here it's only 0.29 or 0.25. So it's clearly we have so kind of like this data set is clearly more complicated data set than the previous one. So the linear model struggles a little bit, but we haven't used everything which we wanted to use in the kind of in squeezing out of the linear regression everything which we can. Okay, so let's check the feature importance again. And because we have also normalized the input values, so the feature importance are playing the role, and so we're also ordering the features. Yeah. And we see that according to this linear model, the most important is the density, and afterwards sugar, and afterwards acidity, and so on and so forth. Okay, so that should tell us something that of the feature importance according to the linear model, but we shouldn't, or at least vanilla linear model, but we shouldn't believe it too much because, the R2 score, which should be a little bit higher, is not very impressive. Okay. There is a strong correlation between the density and residual sugar. Let's go to the density and residual sugar. Yes, 0.84, it's a strong correlation. I completely agree. And in principle, we can try to throw one of those and see does it affect the things or not. Or we can keep them. But, this is, yeah, it's a good observation in the sense like, that means that, in principle, at least in this data set, it means that, they're doing essentially the same job. Or like, this anti-correlation between the alcohol and density. Minus 0.78, it's a strong anti-correlation. But it means that essentially in many ways it's doing the same job. Okay, but let's go into the a little bit more fancy things. So now what we're going, now we're going to do what is called lasso regression. And what is the lasso regression? Can anybody tell me? Yes, good. It's the same linear regression, but just with the penalty. Again, scikit-learn lasso. And what does it tell us? It's a linear model trained not with L2, but with L1 as the regularizer. Okay. So, and we can also see because we have a parameter alpha. Alpha is exactly the hyperparameter. So it's a L1 penalty, not L2, but good. Okay, so now we can try. Of course, it's very easy to train model, but because you see, this is really universal thing here in the sense like, you create a model and you initialize it, fit, X train, Y train, and you get a model. And now what you need to do, you can just see, what is your precision, so what are the coefficients, and you can analyze what are you getting. And so far, this alpha is just, some arbitrary alpha, which we just took from the thin air. Okay. So we could first of all see that suddenly alcohol becomes a much more important coefficient, and the acidity, citric acidity, and these quantities becomes completely irrelevant. And suddenly, yes, alcohol is the most important thing according to this. And that in principle is correlated with our heat map, yeah? So that the alcohol and the rating are the most two correlated features. The anti-correlated is density, but that's again is partially explained that density is also anti-correlated with alcohol content. Okay, and we can check, MSE, and we can check R2 scores, and the R2 scores improved a little bit or not really. What do we have before? Okay, on the training data, it's decreased, but on the test data, it's a little bit improved, okay? But, the question is, because we just took from the thin air alpha parameter, which is a hyperparameter, and in principle, what do we need to do? We need to play the game a little bit more professionally, and that's how exactly now, what exactly we're going to do. We are now going to do we're going to do the search among the different parameters alpha using built-in tools. So we're going to create an array of alphas. Yeah, so what does this do? What is a numpy log space from -6 to 2 to 100? What this comment will do? Any suggestions? What's happening in this array? So if it was a lin space from -6 to 200, what would have happened? We would have a array of the numbers from -6 to 2 with a 200 with a 1/200 increment, yes? So when you have a log space, it means that we're going to have a range from 10 to the -6 to the 10 to the 2 with the increment of also 200, yeah? So we can just for the test of it, we can just try, oops, before we run anything and see what are we getting, yeah? So we're starting from 10 to the -6, and afterwards we're doing small increments until 10 to the 2. Okay, so that allows to cover the range of the values so that we can get enough representation. Okay, let me remove this cell. Okay, so we create the array of alphas, and what are we going to do afterwards? Afterwards, we're going to do the cross-validation, 5-fold cross-validation on the each alpha. And afterwards, we're going to get our the best alpha to fit our model. Okay, so we have some parameters, and what is the best alpha? Our best alpha is looking like this. Okay. So now we can again do the coefficients, and now we get again that the density took over the alcohol. Alcohol falls down in the feature importance. We also get sugar and acidity and pH. Okay, and let's see what is the performance. And we also see that again, the performance on the train get to the without optimization, and on the test it's even fall down a little bit. So essentially you can continue to play this game with a different regularization. What would be the name for the L2? I think that will rich would be L2. Yes, because this is rich is a linear regression, but with L2 regularization. And essentially, we can play the same game with the rich regularization. But we can also put it together. And this is called elastic net. And elastic net is linear regression with both regularizations, L2 and L1. And we can also try to find out what would be the optimal one. Are we good with that? Do you want to try? Before we come to the regressor, which I haven't told you about. So we can play the game with this regularization, and we can just do exactly what is happening here, but now for the ridge regression. So it means for the and let's do it really one-to-one so that we don't confuse ourselves. Okay. And now let's see what can we learn from here. Let's grab some pieces. So let's see what will be our coefficient rankings. And we can also check what do we have in parameter space. Changed everything. Okay. We get L2 regularization coefficients, and let's get also. Okay, my is a little bit boring. Let's look on R2 immediately. Okay, so it doesn't help us. Okay, Tender, you're saying that let's try it. Okay, okay, good. Do CV1. So let's do the same alphas. Yeah, rich CV, okay. It doesn't have a random state. Okay, good. Good. So, what else do we have here? So, if anybody else, Tendo, do you have any results? Have anybody managed to get something which I haven't, not yet, still cooking? Okay, okay. Okay, okay. In that case, let's go. This I have. Wow. You see, here's alpha is almost 1 according to whatever I run here. Okay, maybe that will change something. Okay, let's check this, but afterwards we need just to check. Okay, everywhere. Okay, good. Okay, okay, very similar results, and I assume that probably R2 will also be very similar. Okay, let's see. Okay. Oops. Yeah. Just not much have changed, but that's fine because it's just maybe just indicating to us that the data set is really a little bit more challenging and the linear model can just not catch enough the complexity of the data, which is also fine. Okay, and that's why we have a continuation of the story, which is called random forest. And I will tell you tomorrow how the random forests are built. For us, right now, it doesn't matter because I mean, random forest is a bunch of decision trees, and tomorrow we're going to speak about in the lecture how decision trees are constructed. And this is a very powerful method, but it also requires some games. Just take for us is just another regressor, which is in the same way. We just initialize it, fit, and predict. And that's another beauty because with several of these models, you can really it's in the same style. We can just initialize it and run it. Yes, so random forest regressors, whatever this means, number of estimators, and we just fit and build a regressor. And now we can calculate MSE. And we can not only calculate MSE, but we also could calculate the MSE on the cross-validation score. Yeah, and now what we want, why we don't calculate R2? Let's calculate R2 here as well before we do because you see the next bit is how to optimize it. In this code, let's also build R2 because we have no idea it's very difficult to judge this. Take it in. Take it mean squared error. Okay, so let's add R2 here. Where is our R2 calculations? Yeah, we need to do something like this. Yeah. Take it done. R2 score, and I think I'm missing. Yeah, let's see if it works. Okay, now I'm messing up something. What do I mess up? I have forgot one more bracket. Yeah. Okay. No. What's wrong? Because now it's just a printout. But you see, R2 on the training data, because how much more powerful are these structures is, which I will tell you about tomorrow. Because before we have 0, what is this 229, and now we're 0.93. So it's a substantial jump forward in our performance of the algorithm. Okay, so let's add scoring. By mean, we would work here. Mean squared error. I'm not sure that it will work here as is. Let's just do it on the test for simplicity because it's a mean. Okay, I need to think how to do that, but this I can do easily. Okay. And again, I forget in the bracket. And here, comma 3. Oops, too many arguments. It happens. What do I mess up? This is this. Yeah, okay. Is it like this? Yeah, like this. Yeah. Okay. So, wow. On the training data, we are doing quite nice, but on the test data, we improved substantially compared to what we have, but we're definitely not doing. So we're probably, a little bit overfitting here. That's also strange because we don't have so many leaves. Okay. But at least this is a very, very big progress already compared to what we have before. And let's see what can we get by just playing the game of the optimizing parameters of the forest. So we have the following things: max depth, and we're going to explain to you tomorrow what does it mean, but it's essentially mean that how many layers of the in the trees you can have, and how many features is going to grab. And I wanted to warn you not to run very fast on your computer this code, because it might take some time. Because what this code is now going to do, it's now going to go through the and it's a grid search, so it's going to go through the whole values of the max depth parameter from 10 to 25 or from 10 to 24, yeah, and with the max features between 6 and 11, yeah. So this number of jobs equal to -1, this is usually the statement that you can use whatever the cores are available. So we can just run it, and let's see how many mistakes I'm going to get. And yes, I hear that my computer starts thinking. Okay, good. But okay, I'm done. So locally best parameters. Okay, yes, it's still 21 max depth and max features. And now we can try to estimate the values on that. Okay, we have given some mean squared error. And we can also see, and okay, now we know how to do R2 scoring. Okay, so we get a cross-validation score on the training data like this, and the R2 is exactly as we had before, essentially, yeah? But it's already, no, it's a little bit better. So you see, we managed to improve our kind of our indicators. Okay, so we can what are we going to do now? Now we're going to do the importance. Yeah. So we have a score names, and now let's do the importance parameters again. And the random forest is thinking that the most important is alcohol, and afterwards acidity, density, and so on and so forth. And as I mentioned to you, this really could be an important bit for if you want to build the model of your machine learning system. Okay, so and you can do more optimizations. Let's not run it. You can run it by yourself, and you can try to run this notebook to the end. But let's make one observation. So what do we want to predict? We wanted to predict the wine quality, which is not a regression problem, yes, because the wine quality is 1, 2, 3, 4, 5, 6, 7, and so on. So in principle, it's a classification problem, but we were trying to predict it using the regression approach. And, it's got pushes somewhere, but you see it still gives us a quite diverse thing because we're trying to use regression. And in the other notebook, which is available, which is an advanced example wine, it's a classification. So it's absolutely the same, but now we don't try to play the game of regression to predict, the discrete values. As you see, you can play this game and you can reach some precision, but because you're intrinsically trying to predict using the methods for prediction of continuous values, you're trying to predict the discrete ones, it's not always work nicely. So that's why one need to use classification approaches. So let's go for the classification. Absolutely the same in the beginning because not much have changed. oops, our heat map. Okay, so we need again to do the train-training split. We need to do the scalar. And I think, yes, somebody asked before the break, should we always apply a standard scalar by default? And yes, I think it's a good idea to apply standard scalar by default, unless there is some very special reasons why you don't want to do it. But it's a good practice to apply it by default, as you see, like it's done here. So you have done splitting and you immediately normalize your data, because in that case, as I mentioned, one of the reasons in this particular situation, so that that the coefficients which you can extract from the system, they could be interpretable. Because if we don't normalize the input features, it's very difficult to interpret the coefficients which you have in the system. In neural networks, it becomes even more important, because over there, the non-normalized input features could lead you to the big imbalance in the weights of the neural network, which will be another disaster for the training algorithm. Okay. Again, so we can check again. So what is the stupidest approach we can have with a linear regression? Okay, and we've seen it already. Okay, so but this is just repeating the part of it linear regressions. We don't need to do it. Yeah, let's go directly into the classification. Yes, so let's run this bit because we've seen it already. Yes, so instead of random forest regressor, we're using a random forest classifier, and we're fitting train data to the Y train. So I think that suggests that we do something like this. So the first of all, what we can do, we can produce that object which I mentioned to you already. So we can calculate precision, recall, F1 score, and so on, but we can also produce the confusion matrix. Yeah. So, and essentially what the confusion matrix is telling us, it's telling us, when the score was, what is the range of the scores? And do we have it somewhere? No, this is just the head, and what is in 4? No, let's add something. What it was. Data dot something like this, yeah? Yeah, so data dot describe, and let's see what are the scores. Yeah, the scores are minimum is 3, maximum is 9. Yeah. So and this is our, so it's essentially, oops, where we were. Sorry, where? No. We were here, yes. Because this is on the training data, but that's boring. But so this is from 3 to 9, yeah? And what we could see that the diagonal elements is really true positives in the corresponding classes, yeah? The off-diagonal elements are telling us what is predicted in the corresponding adjacent classes of diagonal. So this means that, here 140 times it was predicted instead of this class, it was in this class. Yeah, so and we can calculate, the average accuracies or weighted averages and so on. And we can judge by behavior, but essentially we can calculate, the accuracy scores, but they behave in the very, but as I mentioned to you, this in principle here we have much more information, and this is a very crude measure because every accuracy score on the training data, because it was here, was perfect. Everything on the training data which was predicted perfectly, because you see the confusion matrix is diagonal, but on the test data, we get the off-diagonal elements in the confusion matrix, which means that we have mistakes as it's expected. And the crude measure of accuracy score on the test data is 67%, which is higher than our whatever the art. Of course, you cannot compare it like that to the to the regression predictions, but at least R2 have a maximum of 1, and you can in some things in some way think that this is kind of we get the precision on the unknown test data essentially 67 or 68%. And again, it was out of the box random forest classifier. You can play the game with the grid search, and you can do the calculations, and you can see are you increasing the matrices or not, and in the metrics do you increase the precision or not. And again, you need to see precision recall or F1 score and how that's behave and how that's evolved, and how to interpret it. But all the most of the data will be hidden exactly in these confusion matrices. Okay, and if we do again the scoring of the importance, we'll see that again, that alcohol is the most important, and the several few other have a comparable feature importance things. So I suggest that you really try to run it. Don't get a little bit confused because you don't yet know what is the random forest, because tomorrow I will tell you a little bit what are the decision trees, and the random forest is just a bunch of the decision trees, which are just picked with the random subsets of the decision trees. And I will explain to you how the decision trees are collected and what is the ideas behind how we build the decision trees, and why the decision trees, as you've seen for these classification tasks, are quite efficient. Okay. So, do we have any questions? Have anybody tried to run it? And are you still cooking? Okay. So then, what have you tried to run? I still try to run it on the regressor side. Because but you see, it's jumping between the alcohol and density as a function of training, because you see alcohol and density are quite or anti-correlated, but quite strongly, because they have a correlation of 78%. And okay, it's negative correlation, but the idea is like they are also in some way reflecting a very similar matters. Okay, using the lasso model, yeah. But again, the problem with the lasso model, and also the problem with that regression things is that we're trying to predict using the method for the prediction of the continuous value. We're trying to predict integer value or discrete values. What I suggest that you try to do, maybe you can try by yourself to do the sigmoid. Can we use a sigmoid for? No, we don't have here. But in that case, it should be something like a softmax. Yeah, so did they have something like that here? Okay, not a linear model. We need softmax. And sample gradient boosting, probability calibration. No, I don't want the neural network models. Yeah, I want a logistic regression, but with the logistic regression for the classification. Which classic? No. Okay. No, because how to do it with the neural networks, we'll see something like that tomorrow, but I want something, okay, rich classifier will be the linear classifier with the We can try the linear classifier, but does it support, is it a binary classifier or arbitrary classifier? Yeah, I mean, it's a binary classifier. That's boring. Okay, perceptron, probably. Linear model perceptron, because perceptron is okay, okay. Okay, so how did we go from the wine dataset being a regression game to a classification game? And what attribute are we classifying for the random forest? Okay, that's a good question. It means that we're a little bit lost, but that's fine. Okay, so let's go to the beginning of the data set. So what is the data set? The data set is the bunch of characteristics of the wine, plus it's a human rating of the wines. And the human rating is coming in the integers. And in this data set, it's from 3 to 9. And we start with regression because the regression, that's what we were doing. But eventually, if I give this is exactly the regression thing. If you go to the end of so if I plot the graph of the actual wine quality against predicted wine quality, yes, with all the methods which you try with the regression, what we see that, the actual wine quality is, of course, is the integers, 3, 4, 5, 6, 7, 8, 9, yeah? But what the regressor is giving you real number, somewhere within the range of what is possible. And of course, this is not right, so that, for the wine quality 4, we get a range of the values. We're supposed to get 4 or 3 or 5 or 6, because there is no interpretation for what predicted wine quality 4.5 means. And that is why we play a little bit of regression game. We've seen that, you can squeeze a little bit, but eventually it should not be treated as a regression problem, because we're not trying to predict a continuous real value. What we're trying to predict, we're trying to predict number, which is a discrete number, or class. Is it a class 3, class 4, or class for the quality 3, class for the quality 4, class for the quality 5, 6, 7, 8, or 9. So we have 6 classes, yes? 7 classes, which are specified by the corresponding quality, and that's what we're supposed to do. We're not supposed to predict the continuous value, we're supposed to predict the discrete value. And in that case, this problem is called multi-class classification. And that's how we jump into this one. And that's why, we didn't try a linear classifier because it's just too boring. And we just immediately went for the random forest classifier because, we've seen that the random forest regressor immediately out of the box, where is our random forest regressor, without any optimizations, yeah? It's out of the box, it beats up the regularized linear models regressor, yeah? Because here we have maximum 0.25, and just with all the optimization, and we try regularization here, regularization there, but it doesn't help. And here we just take a random forest with essentially default parameters, and it's immediately do it twice better. So it means that, random forest as the model family of the machine learning is much more efficient. And it is much more efficient. And the reason why we're going to discuss tomorrow. Yeah, of course, I will share the code. Yes, I will share the code, but, reach and this kind of like, I don't know why they call it as a special function. It's just the lasso, and reach is just the same linear model as we have in the lectures, but lasso is with L1 regularization and reach is with L2 regularization. Because linear model or linear regressor like this doesn't have a regularization built in. So again, if we just go to into here, into the linear regression, we don't have an option for regularization, because on some design decision of this standard basic machine learning package for the Python scikit-learn, somebody decided that the linear regression with regularization should have a different name, and that's the only difference. And CV is built in that cross validation, which I also mentioned. So what it's doing this lasso CV or rich CV, essentially, what does it do? We need to calculate the linear regression with regularization with the corresponding value of alpha from this interval. Yeah. And it's evaluating it with respect to the 5-fold cross-validation. You remember that in the lectures I have that picture with the slices and blocks where we have a test set is here and the data and validation, and we shuffle them around. So it's doing it in the 5-fold, not the 3-fold as I have in the lecture. It's doing it in a 5-fold cross-validation, which is of course is more precise, and it's doing it for each alpha. And as a result, it select what is the best alpha. And afterwards, we can choose it. And that is it.
Okay, is it a best time to end the lecture for today?
I think so, because some people already writing in the chat it's 4 o'clock.
Thank you, Ilya, and thank you, everyone. We resume again tomorrow morning, 9:30 sharp.
Okay.
And please don't forget to complete the quiz. Thank you. Bye, everyone.
Okay, thank you. Bye-bye.